All right, everybody, if you could take your seats, please. We are starting the afternoon session on AI systems. We're going to start with our featured talk from Jun Yang, Senior Director of Compute Architecture at NVIDIA, on using agents to build production AI systems, lessons, pitfalls, and limits.
Awesome. Yeah. And thanks for everyone. And this is Jun Yang from NVIDIA. And I'm glad to be here to share some of our experience of using AI agent for our production AI systems. And let me jump into the main topic. And firstly, there's no doubt agent become a very important and popular technique. And also being a technique, it has its own temper and styles. And to make sure we can use it efficiently, we need to make sure we can leverage advantage and the disadvantage as well. And also there can be very big difference between using AI to build some one-off showcase compared with building a production usage. And for production scenarios, we care a lot about things like maintainability and controllability and completeness, and which can be different from building a one-off demo. And this can impose additional requirement and constraint for us when we try to use agent. And here I will provide some examples to try to illustrate our experience of using agent for our production AI system. And there are around 3 examples about inference, one about training. And for inference, we are choosing the 1030M, and which is NVIDIA-powered large language model inference frameworks. And this has been used by a lot of customers, and also it has been used to support a bunch of key benchmark submissions like MLPerf and semi-analysis and artificial analysis. So this is indeed a production-grade software, and this can impose additional challenge for us to use agent. And the first example is to build an agent-based bug fixing Autobot to make sure we can release our burden from the daily bug fixing duties. And the workflow is relatively straightforward. On the left part, we have the agent flow starting from the bug analysis, then do the bug reproducing. After we are confident that the bug is reproducible, we will enter into the bug fix status by the agent. Then the fix will go through the review phase, still by the agent. And after the agent feels comfortable with the code fix, we will enter into the verification phase, still by agent. After verification is done, we can mark the agent fix phase as done. Then we enter into the human phase. And the human here need to review the code carefully to make sure the bug fix is not a reward hacking, it's not a hacky, and it can be complete enough. And also sometimes the human need to provide feedbacks to the agent workflow to make sure the agent can continue iteration until it finally converges. And here is a dashboard about the bug fix agent. And on the top part, we can see that among the 800 bugs, there are around 313 bugs, which already have the fix from the agent. And if we zoom in further into the bottom, we can see that among the 313 bug fix from agent, only 73 of them have been accepted and landed to our main branch. And there are more than 100 fixes which can be rejected by human because we feel the fix is not complete enough, or maybe too reward hacking, too superficial, is not great. This indeed is a very concrete example indicating the gap between production requirement and what agent can do. And this is also the area we are keeping improving to increase the ratio of the bug fix, which can be finally landed to our main branch. And another example is about using agent to try to increase our velocity of supporting new model in 1030M. And there are new models coming almost every month, sometimes every week. And we want to make sure we can support a new model quickly. And so we build an agent-based modeling tool to try to increase velocity. On the left part is a basic user workflow. We provide a user command line called model dash and bring up. And the user just need to specify their model definition, their criteria into the task YAML file, then can fed into the agent flow and can run through the agent process. And to make sure human can do the intervention properly and the human can interrupt the agent execution process with providing his feedback, and then can retrigger the execution to make sure the agent can be steered towards the right direction we want. And on the right part, we can have a zoom-in understanding about the basic agent flow. This is also a very typical multi-agent workflow. We have the plan phase, we have the implementation phase. For the plan phase, we have the plan generator, we also have the plan reviewer. And for the implementation phase, we have the coder and reviewer and the QA. And we on purpose try to divide the responsibility into several sub-agents to make sure each agent can be very focused, they can use their content effectively, and also they can share the common information through the intermediate files. They can work together as a team. And here's an example. And here we are using the Gemma 4 from Google as an example to demonstrate the effectiveness of the model agent. And in the x-axis is the iteration number from 0 to 175. And on the y-axis is the QA score, and the higher the better. And we can see that starting from the planner, it will trigger execution. Then the coder will have a multiple iteration with the reviewer. Finally, reviewer thinks it's OK. It can pass the board to the QA to do the evaluation. Then QA can send the result back to the coder. Coder will do it again and again, and there can be intense interaction between the coder, reviewer, and the QA. Finally, it can be converged. And here's another example on top of that one. And in this figure, we just add another plan reviewer phase, which we found is very effective for us to improve our token efficiency. And by introducing the additional plan reviewer, we found we can converge with the same quality with just 35 iterations, which can save our tokens. And the next example is also for Gemma 4 model. And when we finish the new model bring up based on agent, we want to use agent to do performance improvement. And here we just start from a low performance baseline with doing 3 additional iterations. For the second and the third iterations, we do have a bunch of optimization finished. And for the fourth iteration, it finally become converged. So we just stop the optimization process. And for the second and the third iteration, we can notice that the agent will create some cookbook. The cookbook consists of the optimization experience accumulated by the team during the past. We just prepare them in a structured way, so agent can use them. We can see that in the second iteration, the agent will create some cookbook about who's the performance optimization, then apply to the final optimization. In the third iteration, the agent will create some cookbook about CUDA graph, then finally apply to the optimization. And also we can notice that there are a bunch of optimization and have been done, but finally not accepted because due to that the performance again is very marginal. That's decided by the agent workflow. And next one is about training. And for training, although it has something in common with the inference, also there are some different characteristics. So we are still using different workflow to optimize the performance for inference and training respectively. And for training, initially we started from building a deep agent-based agent workflow. Eventually, we moved towards building a very lightweight harness on top of the general coding agent because we found the evolution of the general coding agent actually can take over something we have done before based on deep agent. So we want to make sure our agent flow can be lightweight and adaptive, so we can leverage the advances of the general coding agent and foundation model. And the basic architecture of the training proof agent is very similar like before, and there are some additional things we added into the training agent flow, such as the kernel arena, in which we try to reuse our history kernels to make it easier for us to generate future kernels. And also we have a learning feedback loop in which the agent can do the trace analysis about the past execution, and the human can do the review, then we can just feed into the agent flow to iterate the training agent. Also, we have built an evaluation toolkit, which can be used to evaluate the effectiveness of the agent workflow. So when we add a new skill, add some new sub-agent, we can be very certain that it will not introduce too much regressions. But it's not very ideal. We are still trying to figure out what is the best way to defend the agent system evolution. And here is an example by using the Flux model, which is a vision transform model, to demonstrate the effectiveness of the training proof agent. And this model actually has a very good performance baseline based on human observation. And starting from the beginning, it has tried more than 120 experiments, and some of them will be OOM, and some of them can run through but will be rejected, and some will be kept. Finally, 20 will be kept, with totally bringing around 20% performance improvement, which is a very decent number considering we are using a very strong baseline. And finally, let me make a conclusion about some lessons, pitfalls, and limits we learned. And firstly, and the nature of agent intelligence is very different from human intelligence. It's by nature is a probabilistic-based process. So when we design anything, we should take that into consideration to make sure we can use it as an advantage and avoid its disadvantage. And the second thing is that when we are trying to build agent, we should make sure we are not building a very heavy harness. Rather, we should try to make sure the customized agent workflow should be as lightweight as possible, so we can be able to leverage the future evolution of the general coding agent and the foundation model. And also, there are some interesting trade-offs we should consider. For example, and how to make sure we can balance between the fully autonomous agent plus versus the human plus the agent. Yeah, and on the one hand, we want to make sure we can automate everything as much as possible. On the other hand, we found that it's not rare. When we try to combine human plus agent, it can be much more efficient in terms of token efficiency and iteration speed. The second thing is that for production, usually we want to centralize our logic to make sure they can be used by different places. But we found it's interesting to notice, due to that agent can write code so fast, so human plus local custom agent can sometimes work more efficiently than the centralized agent. So we should make sure we are aware there isn't a single silver bullet. And lastly is that we should make sure we balance between customized agent plus the lightweight harness to make sure we can quickly evolve with the new advantage of the foundation model and the general code agent. Yeah, and with that, I can conclude my sharing. Thank you.
And next we have Rick Crawford, Field CTO for Postman, speaking on from agent demos to production, how Postman is building reliable AI agentic infrastructure.
Thank you. Again, I appreciate all of you taking the time to learn about how we went from prototype to production and delivered an agent that's really driving value within Postman. This is a curve that some of you out there that are building agents are probably familiar with. We went from being an organization that was very agent first in terms of doing development, but we recognized that we wanted to start creating runtime agents that would make decisions or help us within the organization. So we started to prototype and identify different areas within the business that we might be able to impact. From that, we started getting some initial excitement, whether it be from our CEO or the board, and they came to us and said, hey, we really want to move and take some of these and implement them within our organization. But then the bigger challenge comes, all right, well, how do I measure this? How do I manage this? How do I make sure that we're delivering something that we can maintain? So this is where things such as determining ROI and runbooks start coming into play. So the problem space that we wanted to address, in this case, was enterprise sales. And the benefit of this is a very well-defined process. From identifying an opportunity to renewing that deal, there's steps that would go along in that. And through that, there's a large number of teams that are working together. The challenges that we're running into is these teams have a hard time in terms of handing off that context of information amongst each other. And when you look down in terms of the number of systems that we're using that pull in, that these members and these teams are working with, it's just a swarm of systems, right? And the hard part is figuring out, well, what are the relationships of data between them? Ultimately, in the end, we end up with this opaque process where at every step of the way, there's some context that gets lost. And so from our organization's perspective, we wanted to figure out, hey, can we create an agent that can help us through all the phases of the sales process? So we did what every engineering organization would do. We had a hackathon. So we opened this up to our engineers, and over 30 hours, they created a number of agents. But what you see here is just a swarm of different systems and connections and agents that were created. Ultimately, in the end, we identified, hey, there's this win-loss agent that's actually able to give us some really interesting results. And from this, we identified 3 core problems. First, the core problem is that we found that the more discrete the more deterministic the outcome, the better the agent was. And in case of the win-loss agent, I could get something such as here's the reasons why we lost this particular account, and I could work back from the reasoning in terms of the results I got back from the agent and say, yeah, that looks about right. Maybe our price was too high and we ended up losing that deal. But if I were to ask that same agent, all right, well, what's the best way in terms of generating leads? It kind of went off the rail. It would start generating results that were very hard for us to determine, is this right or not? The other thing we found is depending on the complexity of the model, the reasoning that came back was much, much better, but also the confusion in terms of understanding those results became much, much harder. The second thing is this is really a compounding problem. Those of you that have built microservices architecture probably recognize this. A2A and agents community to agents, what we were recognizing is that we were ending up with both compounding cost and compounding confusion. And the challenges in terms of the handoffs and testing between these agents became a much bigger problem. And then finally, one of the other things that we recognize is that this is a decomposition problem. What we were doing is we were creating individual agents, and what we didn't recognize is that all these agents were part of the same domain. If there's any design patterns, Martin Fowler fans out there, you probably recognize this pattern as decomposition. What we recognize is the interface between these systems and the handoff of context that was the biggest challenge. So we had these three problems, and what we did is we came up with a framework of 4 solutions to address it. At the foundation, we created a monolith agent. This agent had an understanding of all the knowledge and information that is available as it related to the sales process. Salesforce, Gong calls, it could pull in the transcripts and I can ask it really interesting questions and get interesting results. So, again, this was a great co-pilot, it was a great answer generator, but the challenge we ran into is that, if there were some gray areas, it would start making things up. And it was a great generalist, but if I started asking it more specialized questions, it just had too much information and it wasn't able to give us the right result. So we built off of this. The next stage was the decomposition component. And there's 2 key pieces that we implemented here. One is the hallucination layer. Don't recommend something unless you have a clear understanding of where you're getting that information from. And if you don't have it, you need to really explain why you came up with that result. If it's not able to do either of those things, we would just ignore it. And then on top of it, we wanted to create those domain-specific agents. And this was not a coding task. These are actually prompts where I can go in and say, hey, I'm a seller, here's the things I would typically do. And it would go out and it would start answering the questions as it related to that persona. So it sharpened the output and it stopped doing a lot of the hallucinations, but it was confidently wrong. Knowledge and intelligence does not mean strategy. So if I were to ask a sales agent, what persona should I sell to? Any guesses out there in the audience? Which persona would typically be responsible for buying software? Perfect, yes, exactly. So it would come back and say, sell to procurement every time. If I went into my customers and said, hey, I'm going to sell to your procurement organization, they'd laugh us out of the room. So that's where we started to identify the teams that own that strategic content, and we put them in charge of adding that information. So in this case, the sales team would go in and add their account plans. The field engineering organization would add things such as how their solutions plays. And from this, we started to get more and more strategically relevant information in these agents, and the outputs were becoming more and more important. But the challenge is at this point, I had this super agent that had understanding of my entire organization, but there were no controls in place. And that's where we implemented this last layer, which is beyond the model of determining is this right or not, or is this true or not. We needed to add another layer and say, hey, is this content related to the job that's requesting it? So that way, if I went to the CTO agent, that's not going to give me all information as it relates to the P&L of the business. It would take into account my context and my job role and only give me that information that was relevant to me. But what this has done is it identified a couple of areas that we really wanted to lean into in terms of developing additional agents. And really, we've identified what we call this agent autonomy curve. And at each steps of these, it determines, is it the human or the agent that makes the decision? There's 2 decisions that have to happen. Who's going to request the information and who determines when to promote it? At the help piece, the human's involved in both of those. I ask the question and I analyze the result. The recommendations piece, the agent starts doing that. But where the biggest step change happens is between that act and own piece, where on the act piece, the agent is doing both sides of that equation within some guardrails, and ultimately, the own piece is what we're all developing towards, which is having long-running agents that will go and own the entire ecosystem. Now, what we saw from this was really surprising. We started getting compounding value within our organization. We went from building an agent, taking a hackathon in 30 hours, down to now we have this framework where within a matter of hours, someone can go in and create the guardrails and then build off this body of knowledge that we have. And on the consumption front, we went from just having a select audience of users who are taking advantage of these agents to now the entire organization being able to identify how they too can get value from it. So we got a compounding value in terms of the time it took to develop these agents, and a compounding value in terms of the people that are getting value of it. And the core benefit of this too is that we also saw a change of behavior in our organization as well. So since the salespeople now know that the context that they create and the questions that they ask also help the underlying value of these agents, we're seeing more discovery go on, and we're seeing better quality of content get created. I'd be remiss to say that we also didn't create a platform to help address this issue. We took this learnings in terms of creating a platform that we were able to build these compounding agents within our organization, and we identified that ultimately in the end, I need to be able to measure the outcomes that are occurring. I need to be able to have a catalog of these agents that are available that my teams can hire, fire, and understand what the impact is, both in terms of the cost and the return on the investment. With that, I appreciate the time today. Thank you very much. And if you have any questions, feel free to just connect with me on LinkedIn.
Next, we have Rahul Bakshi, Director of Applied Science, Edge AI at Amazon, speaking on scale compute to the signal.
All right. So good afternoon, everyone. My name is Rahul, and I lead an applied science team at Amazon that's responsible for building our custom silicon. Our latest generation silicon, AZ3, powered our Echo devices that we launched last fall. So as you can imagine, a lot of my time is spent worrying about edge compute, edge devices, and edge scale processing in general. And that's going to be the theme of my talk today. So we've spent the last few years talking about how do we get more compute to our agents. And that's an important question because it unlocks new capabilities. But I want to flip the question today. What if there wasn't more compute to give to our agents because of physics limitations? And that's going to be one of the themes of my talk. And the other theme is that a lot of these edge agents do not require frontier-level intelligence for compute. And we are able to do some interesting optimizations to build use cases in very, very defined power budgets. All right, let's talk about scaling of compute. How do we give more compute to our agents? One way to do it is by spinning up more data centers. We've all seen the news cycles in the last few years. Amazon, other hyperscalers, neoclouds, everyone's building more and more gigafactories to give more compute to our agents, and that's one lever. But on the other end, there is a real power ceiling. And I will use variable technology as one extreme of that ceiling because the constraints are the hardest there. So if you think about any variable computer, such as a smartwatch, smart glasses, rings, and so on, they typically have around 1 to 1.5 watt of power to work with. And the reason is biological. Human skin cannot tolerate more than 43 degrees centigrade of heat without starting getting burned, and it gets really uncomfortable. So that's the hard ceiling that we have to work with on the edge side. And the asymmetry between the edge and the cloud, I think, is the fertile ground for innovation for next generation hybrid architectures. Let's look at the second observation. If you agree with this ceiling, and if this is the bounds that we have to work with, there are largely 3 tiers of power profiles of what executes on the edge scale devices. At the lowest and most power efficient tier are processing the signals where they originate. So think about tiny wake word detectors, think about event cameras. You detect at the source and you burn minimal energy. At the next level is what do you want to do with that signal? If you have to run some algorithms or if you have to run some tool calling workflows, that requires the next level of energy, still running on edge device, but notice a few orders of magnitude more power that gets burned. And then finally, if the task requires context that's not present on the device, or if it requires world knowledge, then you invoke data center class compute, which is even a few order magnitude more. So what's the takeaway? The takeaway is escalate only when the task calls for it. So the next observation I will share with you will give you the same conclusion, but with a couple of different lenses. So earlier this year, Berkeley has a function calling leaderboard, which tracks the function calling efficiency of different models. And what we saw was that a small language model was able to meet the frontier level performance for function calling task. This task it tracks the primitives of function calling. So the JSON that gets generated has the right functions, right APIs, right parameters. But the point is that for small sets of tasks that are well-defined, we have a pathway of getting frontier-level intelligence on at-scale devices. And look on the right side of the chart. Over the last decade, the cost of transporting 1 bit of data across the wireless networks has gone down many-fold. However, what's not gone down by a similar factor is the cost of radio. So that is, both of these data points are yet another observation on where the partitioning should lie. Escalation to the next tier is expensive, both from an energy and battery life perspective, and should be done only when necessary. Now, for what are the opportunities? I think the loop has been well established for for more than a decade. If you look at the assistants from Amazon, Apple, Meta, most of them have a cascaded tier where you detect the wake words and keep escalating only when necessary. What is missing is a composable runtime, and that's one call to action for this audience. So let's take an example where you ask your assistant, hey, what time's my flight? Is it late? Now, if the runtime had the intelligence to know that for doing this activity, I don't need to turn on any of the perception sensors, cameras, microphones. All I need is turn on the radio and do an API call. Then a power budget can be created, and the function calling can take a certain dynamic schedule. So that's on the runtime side. A couple of other call for actions. I think benchmarks, there's a good opportunity to enhance those, and Berkeley is a fertile ground for that. Berkeley has the function calling benchmark. I think there's an opportunity to extend those to also include joules per task, not just number of parameters and accuracy. I think energy is also an important frontier. We talked about the runtime, and then finally to the silicon developers in the audience, I'd recommend pushing the frontiers, lower the resting power so that we can build more efficient agents for the edge. And that's a wrap. Thank you so much.
We now have John Liu, Principal Product Manager at AWS on looping for model optimization.
All right, good afternoon. Yep, John Liu, Principal Product Manager for AWS Trainium. And today we're going to talk about looping and model optimization on AWS Trainium, which is the custom AI accelerator used by leading frontier labs such as Anthropic and OpenAI. So why is this relevant now? And when you think of it there's probably two angles, right? First, from the business angle. As Peter DeSantis mentioned yesterday's keynote, the future of agentic workloads is going to be one with many chips, custom built for the different purposes of that agentic workload. Now, at the same time, agentic harnesses, agentic solutions, they've been gaining in adoption, they've been getting more mature. As you'll see, the model optimization path on custom hardware is actually very well suited for this type of workload. So what does a typical model optimization loop look like? Well, you start by creating a functional model on the custom hardware, and then you take some knobs on the model level and kind of harness level type of configurations, such as changing the parallelisms, changing the sequence lengths, batch sizes, and then you profile that, right? You profile and see how the performance is, and based on that, you go through a loop. You change more things. At a certain level, you're going to maximize what you can get from these out-of-box knobs. So then you drop into the kernel development. And think of kernels just as custom functions that let you unlock more performance on hardware. Again, you tune those, you profile it, and you have that second loop. But you're not done yet. Once that kernel is optimized, you actually need to do end-to-end model evaluation as well, just to make sure it works. And now you complete yet another loop. So you can see this is actually a multi-layer, multi-variable type of optimization problem, very well suited for looping. And we've actually released some open source agents and skills to help our customers turn what took weeks into pretty much hours. These skills help people create functional models on AWS Trainium, author kernels, profile kernels, and now we're working on the optimization loop as well. So let's dive a little deep into one of these optimization loops, which is the kernel optimization loop. And this is a common setup, right? We use what's called a planner and executor type of model. And the goal that we try to loop towards is what's the gap towards the maximum performance that that hardware can achieve on your particular model. So starting from step 0, there's another loop that identifies for a given inference workload, what's the best settings? And it passes that to our planner agent. That's step 1. The planner agent looks at this, and it measures the gap to roofline, and it looks at its local knowledge base and identifies the best optimization campaigns. It passes that to the executor agents, which runs these campaigns, and then based on those outcomes, it records the outcomes in the knowledge base. Did this kernel work? Did it fail? What were the constraints? And then we measure the performance of that end-to-end model. And finally, based on those outcomes, we decide to promote or reject that kernel. And of course, update the knowledge base as well. And that completes the loop. So I want to share some insights that we have from building these loops. And hopefully they're applying to not just the specialized domains, but everyone's loops. And number one, a recurrent theme that you've heard from is agents are very sophisticated in coming up with cheating, right? The standard approach of telling agents don't cheat, that's not enough. The mitigations of creating held-out data sets and making sure that agents aren't memorizing things, that's the baseline. What you need to think about is every single part of your agentic workload is going to be manipulated by that agent, especially the area where you're measuring performance. The second insight, which is whenever your agent fails, don't go through and just start fixing that agent itself. Check the visibility scope. Right? In one of our examples, that agent was actually maximizing local memory usage for the kernel, which is the right decision. But it affected all the shared memory usage for the other kernels that were running on the model. So check your visibility scope as you're designing your agent actions. Third, when you're creating these knowledge bases, and whenever something goes wrong, check to see if one of your existing rules caused the error. Edit and delete that rule instead of just adding yet another rule, because now you're going to start confusing the agent with more rules. And on a related topic, that knowledge base that you have has a shelf life. Right. In specialized domains, this knowledge base is very helpful to get your agent started. But as the model's general training catches up, now you're going to have some kind of conflict. Your agent's going to get confused. Should I use the knowledge base or should I use the model training? So a good practice is to constantly remove the knowledge base and check the performance of your agent. And if it improves, it's time to prune that knowledge base. Finally, in specialized domain, there's no standard data set or benchmark for success. So as you're designing your process for improving things, you're also defining what that better thing is. And you have to design the benchmark and evaluation as a first-class design component before you get to the rest of your loop, because it affects how that loop operates. So, a very short amount of time. If you want to learn more, check out our blog, check out our GitHub. And thank you very much for your time.
We now welcome Jong-Rose Kim, Head of AI Systems Infra at SK Hynix on disaggregated LLM serving with shared memory KV cache at rack scale.
Hello everyone, my name is Jong-Rose Kim, from SK Hynix. I'm Senior Director, and I also working for the SRC as a SAP. So today, I want to talk about the new memory as a physically disaggregated pooled memory. So this is a memory pool disaggregated from the servers. So in this diagram, so node means server, and this is a memory pool box is really a disaggregated memory pool. So multiple server can use this memory pool at the same time with the two modes. The first one is a memory pooling. So each node can dynamically allocate the additional memory. But that memory region is isolated between nodes. But as a sharing mode is a multiple node can see the same memory address space. So each node can access the same data. So we are very interested in this sharing feature. So we quickly integrated this memory pool with the real LLM serving system. So we successfully deployed this system, and we demonstrated at the last year so many events. So in this diagram, so there are 4 servers, and 4 servers can work with so many LLM serving components. And the middle of servers, middle of rack, that is a Niagara, that is a real physical as a pooled memory. In this scenario, in this demo scenario, so there is we use that memory pool for transferring the key value cache. At first, after prepare, we need to deliver the key value cache to the decoding side. So by using the 2 memory copy, store and load, we can deliver the key value cache to the decoding node. But we can find that in this system, the all key value cache can be stored in the memory pool. So we can reuse it for the next request without some additional storing operation for reusing. So as a result, we can improve the system performance compared with the all recomputation. This is NXL. And LM cache is in-server is a DRAM-based key value cache storing. But important part is why we can have this kind of benefit. The first one is a fast inter-server is a data movement by using the pooled memory. Yeah, instead of using the TCP/IP, we generally use the RDMA. This is fast. But this pooled memory-based data sharing is faster than RDMA, so we can have a performance improvement for the LLM serving system. Second one is by using the pooled memory-based data sharing, so we can have some another benefit. We can release the GPU HBM immediately by operating the key value cache to the pooled memory. So if there is if there is out of memory at the decoding side and prepare side, but we can continuously do the prepare because we already uploaded that key value cache to the pooled memory side. And so to store the key value cache and for reuse the key value cache, there are many contention can be happened in the GPU side, the PCI bandwidth, and network side, the PCI bandwidth. There are many contention, but by using our pooled memory-based data sharing and transfers, we can remove this kind of additional contention. So we deployed as in the Agentic AI serving system, so we should reuse the large amount of key value cache. So we applied this system, we applied the Agentic AI serving system to the pooled memory environment, and we can find this kind of performance improvement compared with the Mooncake and LM cache. That is a very initial performance number, but by end of this year, I'm working with many collaboration parties, around 25 parties. So we are preparing the 5 more system POC, such as multimodal serving and long-term memory management. And we are trying to build the real system with the pooled memory for the HPC US-based national lab system. So yeah, let's see so how the pooled memory can change the AI system. That's it. Thank you.
Now welcome Ben, Senior Director, Core ML at Together AI and Unified Orchestration System for Verifier-Free Evolution.
Thank you. So today I'll be talking about Squeeze Evolve, our approach for unified multimodal orchestration system for verifier-free evolution with applications for scientific discovery. So let's take a look at the components for scientific discovery. This one is taken from SkyDiscover. So there are 4 distinct components. The first one is context builder. The context builder's goal is to provide problem context as well as injecting ideas, guidance, reflections of previous mistakes and success into the prompt. And the prompt is given to a solution generator, in this case LLM, where it has access to environments such as execution or ability to look up the web. And solutions are passed to evaluator, where evaluator's goal is to provide scores, provide logs, provide feedback or necessary artifacts. And these solutions and metadata are passed to solution selector, which selects sample solutions to be passed to context builder so that we can use it in the next loop. Prior methods for discovery frameworks often require external evaluator. So in the domain of physical science, for example, evaluators can be costly and time-consuming. So our goal is to answer the question of what would be the upper bound of evolution system without verification in the loop, and can we also reduce costs? One of the problems for evolution system is degradation of solutions. Long story short, if we use a single model to perform evolution, it's often the case degrading the performance because there's only so much entropy and only so much creativeness in a single model. So our solution is to use multiple models to tackle this diversity problem. So in this case, multiple solutions or multiple generations are selected from previous generations and current generations and assign probability fitness scores. In this case, we use token log probabilities or diversities of solutions as a fitness function. And in order to increase diversity, we pass the difficult solutions to expensive models, similar to single model framework. Whereas if we identify the solutions as being easy enough to evaluate and combine, we pass them to a cheaper model. And in this case, we are able to increase diversity and also increase cost effectiveness. So the result here shows that for the full pipeline with 10 evolution steps with Gemini 3.1 Pro, the accuracy on ArcAGI is 97.5. This is with 10 steps, and cost is around $7 per task. But in the scenario where we use a cheap model in the mix, which is the Gemini 3.0 Flash, we're able to retain the same accuracy with only 2 steps, 2 evolution steps, while achieve cost savings. The dollar per task is around $5.9. Another interesting observation is that in the vision-based task, not having to use the vision component for the aggregator stage also allow us to increase the cost effectiveness significantly. For example, in the red curve here, where we use a strong multimodal model, the performance gets quite high, but also notice that the cumulative dollar per problem is also proportionally high. But in the squeeze evolve method, where we use a combination of powerful model as well as cheaper tier model, we're able to reduce the cost significantly, and in some case, in the heterogeneous case, we're able to outperform the single model scenario. So we're very excited to share this, and this work has been integrated into NVIDIA Dynamo. Huge shout out to NVIDIA, and also we have Cloud Code plugin available. Yeah, thank you so much.
Now we have Tushar Krishna, Associate Professor at Georgia Tech and CEO of Infravana, on how Agentic AI is rewriting the rules of AI infrastructure.
Thank you. I guess I'm audible. So we're at 1:45. I know it's officially the end of this session time, and my superpower as a professor is I can rush through any number of slides in 5 minutes, but I'll try to keep this short and talk you through about how agentic AI is rewriting the rules of AI infrastructure. So we've entered a new era of what's called tokenomics, right, where we essentially feed in AI workflows to our AI systems and outcomes tokens. And essentially, there's a lot of metrics we've started caring about, things like tokens per second, tokens per watt, tokens per dollar. Now, in this ecosystem where you have a workflow on one end and hardware on the other, the software stack that's really in the middle becomes very, very crucial to get token efficiency. Now, a lot of the inference-serving stacks that are out there today were really built, for the chatbot era, right? So essentially, their characteristics are they can run, typically one model at a time, really optimized for static execution paths. Each request is assumed to be independent, a lot of kernel optimizations, and the hardware is primarily homogeneous, right, for the most part, GPUs. Now, of course, we are at the Agentic AI, summit, so the question is, what changes with agents? So there's two core things that we observe as emerging trends that are inevitable. So the first is around dynamism, right? So we've already heard a lot of talks. There's a lot of models. There's tool calls, dynamic fluctuating demands, interdependent tasks, and a lot of workflow level optimizations. And the second key trend, in fact, speakers before me also did a great job talking about this heavy heterogeneity. So there's already, a big use of CPUs for handling, anything that's not an LLM. In addition, there's a lot of other hardware out there that is really specialized and optimized for different parts of the task, right? And what's also interesting is in this agentic era, this is again, a data point I got from, just a talk yesterday from Google. There's 10 to 100x more, computations, compared to a non-agentic workflow. So again, the software stack becomes even more important, right? So it's important for us to now really try to understand what's going on behind the scenes, right? So if we try to demystify all of this, fundamentally, if you go down all the way from the workload to the model layer to the software to the hardware, there are essentially choices across the stack, right? There are tons and tons of choices and optimization opportunities throughout the stack. And if I kind of abstract these out, ultimately what we are trying to do is get, end-to-end service level objectives, which could be related to whatever the agent, cares about for that application. And on the other end, we care about a lot of infra level objectives, right, for running our data centers efficiently. And so now you have this, cross-dependent space, trillions of choices, diverse SLOs, and rapidly evolving components within the stack, right? Which means that, it's kind of almost inevitable that, you would go wrong when you pick something, and the chances of going wrong are actually very high, and the cost of going wrong is even higher. So then the question is, how do you extract token efficiency in this, very, very complex ecosystem, right? So there's a famous quote, right? You can't optimize what you cannot measure. So over the past many years, we've been, working closely with academia, industry partnerships to really understand the end-to-end stack for AI systems, right? All the way from the hardware to the software to all the way to the workloads, right? And we've also worked very closely with a lot of benchmarking and standardization agency to create APIs with which a lot of these benchmarks and tools can work interchangeably. And this has led to massive adoption. So I'll especially call out Chakra, which is an initiative we started with ML Commons. We just released Chakra a few weeks ago at MLSys. So this is basically a benchmarking methodology for distributed AI platforms, and AstraSim, which is a simulation platform for studying distributed AI networks. And with this adoption, what's also interesting is, throughout, a lot of the companies that we've been working with, from hyperscalers to hardware vendors to OEMs to test vendors, one thing that keeps coming out is that the only way to get efficiency is, optimizing across the stack. Optimizing just parts of the stack will not work. So that gets me to, something I'm personally very excited about. So we just started Infravana. This is a company that's built an automated, agent plus hardware-aware full stack optimizer. And we're already seeing, massive speed-ups over the state-of-the-art inference frameworks out there. And, you'll hear a lot more from us as we come out of stealth. So, if you can feel free to find me anytime at the conference, or, email me if you want more, if you have any questions. And I'm happy to, kind of officially call this session to a close. Thank you.
All right, that wraps up our AI systems section. We are now on to enterprise AI, where the first speaker would be Enno Reynes. He is co-founder, CTO of Factory AI, building the software factory.
Hey everybody, excited to chat today about, is it this thing? Oh yeah, great. Excited to chat today about this concept of the software factory and a little bit about what we're doing. And so when I talk about the software factory, I always like to reflect on how insanely quick this entire field has actually evolved, right? 3.5 years ago, basically. We started 3.5 years ago, and back then, autocomplete was basically the only sort of like known workflow for introducing AI into the at least like dev tools that were let's just say like what we now consider to be standard like agentic or semi-agentic LLM based workflows. And so autocomplete moved on to chatbots, chatbots moved on to agents, and agents are now moving into software factories. So what does that actually mean? Well, if the slides were ordered well and that I had sent, my bad, I would be talking about exactly this, which is that a software factory is really this process where signals flow in into sort of your system, right, or your business. These signals could take a lot of different forms, but traditionally, if you're building like, let's say like a piece of software that helps people like manage information, or you're like a school system and you're trying to build some software for that. Maybe you're a financial services firm and you're doing a bunch of stuff to manage transactions. The signals that you're ingesting might be things like customer feedback, internal data telemetry, an executive saying we're going to pivot, right? Like it could be a lot of different things. And all of these signals today, human beings actually triage themselves in their heads. And it's almost never explicitly represented in any like real system. At that point, those signals are then sort of ingested. And luckily, if you're like operating on signals for things like a bug or an error, you hopefully have telemetry for that. But ultimately, that triage process is very human-driven today in almost all organizations. Then you go and you start to plan, and really that's the first time that you start to encode any of this information anywhere. You'll typically do this in something like Jira or maybe Notion, maybe you're doing it in Confluence, but either way, this planning process tends to be fairly unstructured at most organizations, and then you start to move into actually writing the code, validating the code, shipping, deploying, and ultimately with deployed monitored software, it starts to generate more signals. So what's interesting is this implicit feedback loop exists at almost every company building software, and yet an explicit model of this does not really exist anywhere. And so what we've sort of found is that what's interesting about this is that if you think about the hard part of this problem, coding is just not the hard part. It's basically, in fact, the easiest part of this problem. And in fact, all of the other things around actually writing code are the hard part, the part that leads to mess. And I think that when a lot of people think about sort of the velocity aspect of, you have an AI CEO or saying like, oh, AGI's here, it's like 6 months away, you're gonna see 100x productivity, and then you yourself have not seen that at your company. A lot of people are sort of asking the question, why is that? Well, really it's because you're actually only AI-ifying like one narrow slice of this process, and then a lot of it remains a very human-driven, synchronous workflow where you go and you say to a machine something that basically looks like autocomplete. I want the thing, you give it back to me. I send you on a task, it comes back to me, right? And so what we want to do is we want to say, how do we basically design a system that allows signals to flow all the way to deployed software without human intervention, right? And so when I say without human intervention, I don't mean without humans at all being involved in the process, right? And that sort of leads to a lot of the questions that I think people are asking right now, which are probably very hard to read on this slide. And like things like, how do we prevent cost overruns if this fully autonomous system is operating, sort of like without impunity? How do we ensure we have access to the best possible AI systems, regardless of like who wins the model race, who wins sort of the AI layer race, right? You've already heard, I think that last one did a good job of showing how much complexity there is in the vendor ecosystem, right? You don't really want to be making a bet on any one of these things. You just want to be building a system. So how do you do that, right? Also, how does the role of the human evolve in this new system? If you're not intervening as the signal flows all the way to deployed software, what are you doing, right? Well, I think that, and then how does that change the organization? I think that generally you should then be thinking, well, okay, if I'm not doing that, then I'm clearly somehow involved in building this system or maintaining, refining, or evolving the software factory. And that is ultimately the new role for people. And so if you're thinking about what does it mean for me to build, refine, or evolve a software factory, you should be thinking about a couple things of like, one, how should this system be designed? Well, we have a couple of opinions. The first is that you should be model independent, right? Like if you are operating in a world where you're gonna delegate your software factory to a single model vendor, and they're gonna make a ton of arguments that are actually not that compelling, but maybe they'll make compelling arguments that, oh, you have to verticalize aggressively and your agent harness needs to be with the model. We found like empirically that's like very clearly not true. You actually want to aggregate and commoditize that model layer in order for you to have access to the true Pareto frontier of both cost and quality, all right? And so then the second thing is who should own this? Well, we literally make SaaS to help you build this, but I still think that you should be in control of whatever software you use, right? And so we also offer things like on-prem, air-gapped, all the way to basically, you sign a contract and we throw it over and we don't see it again. And that is because we believe you should be the sovereign of your software factory. It's incredibly important that your software factory operates regardless of what vendors come and go, because ultimately your software factory is your company, right? If you build software, you're basically describing the new version of your business. And so it's really important that you're able to maintain and control that. And then the last is you should really be thinking about your software factory as something that operates across every action that takes place inside of your product and engineering organization. So if there is basically any activity, any context, any workflow, that's a part of your software factory. And there's a lot of stuff that you can do, right? Everything from code review to security analysis to testing, documentation, right? Incident response. But at the end of the day, each of these workflows should probably operate with effectively a shared agent core. Because I think that there was actually, I really enjoyed the talk just a bit ago that was talking about this idea of if you have like a ton of different specialized agents, like a code review agent and an incident response agent, you sort of end up in this weird microservice system where you're hyper optimizing each of those agent architectures for what is ultimately one sort of shared workflow, which is gathering information, acting on information on computer systems, and informing the user as it does that, right? And so you really sort of want this singular AI agent system where the context and the workflow changes, right? Code review is obviously a very different workflow from incident response, but ultimately it's actually at a high level, all just gonna be like computer control on top of the agent with context. So using a shared agent core to then operate across many surfaces that your software factory may touch is also super important, right? In a larger organization, you're probably thinking about things like governance. How do we handle, consistency? How do we handle ensuring that, an agent doesn't go and like drop a bunch of tables, right? What about IT ops? A bunch of stuff like this sort of becomes very clear. I would argue that this is ultimately the responsibility of whatever agent platform you're using to enforce all of these standardized controls. And you really should be asking, is there a page called like enterprise controls or organizational controls, and how many are there, right? And if you're not seeing hundreds of different scenarios that an agent platform has gone through in order to basically refine preventing bad things from happening with agents, then I would just start looking out and see like what is out there. There's open source standards. Docker just came out with a really interesting sort of like 35 control system for this, where they said, what are the agent controls that you need inside of an agent platform, sort of vendor neutral. I thought that was like a pretty cool way of delivering that. And so then that sort of leads you to this next interesting point, which is that almost certainly after all this work of talking about agents, you've actually maybe not fixed the biggest problem that's preventing agents from succeeding, which is the state of your environment. And so I always like draw the analogy of human beings. We don't like, when we were 200,000 years ago, we're like not that different. We're pretty much the same humans, more or less, but we're so much more advanced. What happened? Well, we completely changed our environment around us, right? And so yes, you can wait for agents to continue to get better. They will probably continue to get better. But I think that really updating the code base and the engineering system around your software factory is by far the highest leverage changes that you can make. And really that's looking at things like dev reproducibility, environment cleanliness, linting, type checking, quality tests. Really, the actual sort of tidbit would be, what is the amount of, or like, do you have enough deterministic, verifiable feedback loops inside of your organization to give agents the ability to succeed without needing to consult a human, right? So it's one thing if you wait for code review to say that code is not organized well. It's much better to have a deterministic signal that says that code is not organized well, right? And agents can then use that to loop and validate their work until they succeed. So yeah, here's a laundry list of controls that matter, right? Security, governance, and enablement. All of these are super important. I don't want to like blaze through this, but I think it's like the type of thing where you can take a photo. Ultimately, my view is that your agents are going to have access, ultimately in the software factory, that is dangerous. It's just how it's going to happen. Like, it's not really a matter of if, but just when. And so you have to treat them the way that you would human beings, which is you build out systems of control and you build out layers, right? So how do you prevent a human from dropping an important table in your company? Well, you may be relying today on basically telling them not to do that, right? That is actually not good. And probably the analogy that if you've ever thought about building sort of software organizations for more than, say, 50 to 75 people, you start to realize that even 50 to 75 incredibly competent people, someone's going to eventually drop the database, right? And so you really have to think about introducing these agents as sort of scaling up the guardrails, prevention, et cetera, towards what an organization maybe 10 times larger than your current organization would look like, which is sort of interesting, because if you're a 5-person startup, that means you're actually operating at what the controls that maybe a 50-person company would need. If you're a 50-person company, 500 people, right? And so you really have to up-level a lot of the guardrails and the systems that are actually very well established, and I think you don't really need to reinvent the wheel here. You should look at software development best practices and then just ensure that they're being enforced on those agents. And so on that idea, I think that this is like probably the most interesting and evolving part of humans' roles in the software factory. I sort of alluded to this earlier, but we've already just labeled a bunch of things that I'm suggesting that you change, right? This is what we're gonna do. We're gonna say, what are the guardrails that exist? Oh, there aren't guardrails for that. Let's actually implement the guardrails for that. We're gonna look at where agents are failing, and what are we gonna do? We're gonna add context. We're gonna update the workflows that the agents are following. A lot of, actually, like, if you've listen to any talks, and I highly recommend listening to talk about like chip fabricators or any of these really advanced like Industry 4.0 actual real life factories, you start to realize there's like whole dedicated roles of process control, process management, loop management of people who basically just look and say, okay, great, like we lost 10% of the resources due to this bad inefficiency. Let's go fix that part of the factory, and then we're gonna reiterate and sort of refine. We're basically gonna be doing that for software systems. And so I think a lot about this process of how do you observe failures in your software factory? How do you intervene when you are seeing either one, like a one-off, or two, a consistent failure, and three, how do you then refine iteratively those workflows? It ends up kind of, as everything does, boiling down to evals and verifiability. Like, how do you evaluate whether or not a failure happened? The case study here would be code review. Like, pretty much everyone in here who's thinking about a software factory, the first step you can make is building a system that makes you confident to merge maybe 5, then 10, then 50, then 100% of your PRs without human code review. What would that look like? What is that system? And that doesn't mean that you still don't need humans to understand the code changes. That's sort of a separate part. But ultimately, you probably need something like what self-driving cars had, which was, this is kind of dark, but like fatalities on the road. Like, everyone knows when the fatalities on the road drops below, and the order of magnitude is kind of what's interesting. Maybe it's the same as humans, maybe it's 10 times less than humans, but there's some sort of metric where we go, great, we think this is safer than the humans, so we're happy to let this thing start driving. Similarly, with validation, you need to get to the point where you say, what are my metrics that I'm gonna measure to allow that review step to happen without a human in the loop? And maybe you feel that it's like bugs, maybe it's incident responses, incidents, maybe it's MTTR. Maybe you wanna look at a bunch of these things together and say, we think that maybe our system is now safer than humans being involved, so we're gonna let that thing run. And you should probably have engineers thinking about that inside your company. I sort of just alluded to this as well, which is, what are the outcomes then you're measuring? I would be looking at cycle time, I'd be looking at code shelf life, incident time, number of bugs that have occurred. Do not measure tokens. It really does not give you a ton of information or value. And so you can also, though, look at costs in other ways, maybe just like cost per code change, cost per like loop or per week, right? almost treating it in a way that we do humans with salary. And those are the things that you can then measure and iterate and optimize against. So if you take 3 things away, it would be 1, invest in agent readiness. That is super important. We build a product for that, which is pretty cool. 2, govern before you scale. You want to implement all this stuff before you start immediately rolling this out across the whole company. And 3, you got to be thinking about the outcomes that you want to measure in advance. Because I think the last deck just had this. You can't optimize against something that you aren't measuring. So really important to have all this stuff together. And hopefully this was helpful in thinking about building your software factories. Thank you.
We now welcome Anka Goyal, a principal staff software engineer at LinkedIn on infrastructure for long-running agents.
Good afternoon, everyone. I'm Ankit. I'm a principal staff engineer at LinkedIn in the AI platforms team. I'm going to give an overview of our agentic platform and talk about some of the trends we are observing as we scale agent-driven experimentation. So first, I'd like to introduce some of the agents that we are running in production and that have delivered significant business value. So first is model generation. So LinkedIn runs 400 plus models in production that are written in TensorFlow, and we are trying to migrate them to PyTorch. Now, we have written an agentic workflow that can do that, and the challenging part in this agent is ensuring that the new models that we are generating, they perform either on par or better than the production deployed models. And those production deployed models usually have been like human tuned by engineers over like multiple months or even years. The next is performance optimization agent. So this is an agent that we run in our cluster that looks for low utilization jobs. It basically profiles them, benchmarks them. We have a whole knowledge base that our team has collected over the years, and it optimizes them and like creates a pull request for different teams to review. And then finally, to build on top of that, we have an autonomous research agent where engineers can define an objective, and this agent will autonomously do architectural sweeps or hyperparameter tunings to basically optimize for the objective. Now, all these agents sort of have a fundamental life cycle that they share. The first one is an engineer writes a hypothesis, writes an objective, and the agent then forms an hypothesis. It generates the code, runs it on our GPUs, and then the agent evaluates the outcome. Now, this loop can run over hours or even days, continuously, autonomously, without human intervention. Now, with introduction of agents into the infrastructure, we observe like certain shifts in how how to architecture the infrastructure. One is the UX. Traditionally, we focused a lot on creating rich abstractions so that engineers can write their machine learning pipelines or their training loops easily, or how to access data. Those are still important, but that code today is now generated by LLMs. So the focus of our users have sort of shifted towards creating agentic workflows and creating appropriate guardrails so that agents don't deviate from the original task. The other is compute. Engineers typically launched a limited number of long-running jobs in our cluster. A couple of minutes of delay was usually amortized over the run of the training job. Agents, however, can launch hundreds of jobs within a very short period of time, and ranging from like few minutes to hours to even days. And finally, the trust. We kind of inherently trust the code written by humans or engineers. However, agent-generated code needs to run in a very constrained environment. So to support this in our infrastructure, agent is just like any other task. Users write agents as if they're writing any other, like PyTorch or TensorFlow job. The difference is the agent code is untrusted, so it runs in a highly restricted environment, like no egress, no access to credentials, and all the communication goes via our proxies using the agent's own identity. Now, natural language prompts, they tend to not do well when agents are running for long periods of time. So we follow harnesses code approach for all our agents. Each stage is defined in code and has its own responsibilities. And additionally, and more importantly, the scorer and evaluators are also defined in code so that agents don't do reward hacking or they don't diverge from the path. And then we have a whole ecosystem of tasks, memory management, on how do agents share their learnings with other agents of the same type, different type, and then the notifications for human-in-the-loop type of interactions. Now, given these agents can run over long periods of time, we also have a robust checkpointing and restore so that agents can autonomously recover from any failures without any human interventions. Now, as I mentioned, these agents can launch a very large number of jobs, and this creates sort of a bottleneck in our control plane, which has been sort of designed with a lot of abstraction, and those abstractions add up once agents start launching like a lot of jobs. So we've built a customized control plane which maintains like a warm pool of GPU pods, and it can provide a very low latency job launch. Similarly, since we are running agent-generated code, this pool of pods is like highly restricted with like no egress, read-only access to data, and it runs in a highly unprivileged mode. So the impact of agents is clear. The number of experiments in our cluster has grown by 100% over the last 6 months. We are continuously investing in our evaluations so that our experiments can turn to real production value. Additionally, we are investing in SLMs for specialized tasks, and we're also looking into GPU sharing techniques so that we can get more utilization out of our GPUs as they keep getting bigger, but not all the tasks are bigger to utilize the full GPU. So the goal with agents for us is to take more shots at the goal. The more shots at the goal we take, the more improvements we can make to our models, and eventually improving the member experience and providing more business value. So thank you.
And now we have Daniel Homla for lead AI engineer at BMW Research on multi-agent patterns and reliable orchestration.
Hi, everybody. I'm Daniel Homola from BMW Research. The title sounds like a patterns talk, but the core question is simple. In an agentic system or a multi-agent system, the core question is who should handle this piece of work? Reliable orchestration depends on making that choice well, repeatedly at runtime. This is my background. Recently, I'm working on agentic AI architecture, basically system-level architecture for agentic AI customer products and graphical user interface agents, basically computer use agents that operate screens like users do. And for the motivation behind the GUI agent paradigm, you can have a look on this talk that I held last year at AI Engineer Conference if you're interested why an enterprise would consider this technology as one of the agents. Let me run my talk in the multi-agent in-car voice assistant, where we could have 3 agents. You might have navigation agents for finding your route, car control agents for manipulating your windows, seats, climate, and also this, for example, GUI agent, computer use agent that can operate, for example, applications through the screen. Above them, then you have the orchestrator who acts, coordinates the execution, and sometimes combines the results. And after all, the hard part in the orchestration is not the patterns and how do we put stuff between the agents. It's about the delegation choices and the coordination, making it reliably under constantly changing context. And there are many coordination patterns, but they all come down to the delegation decision, to the runtime decision. In a handoff, the control transfers to another agent. In agents as tools, the orchestrator delegates work to the specialized agents and waits for the result. In routing, the classifier or the router dispatches each turn to the specialist. But there are other patterns. Every enterprise defines their patterns in a different naming, but essentially it's the same. It's about the choice. It's about the delegation that we need to do, and it's about which agent or tool should we delegate this piece of work to. And it can all sound like ordinary tool selection, but it isn't. Tool selection is often evaluated against one ground truth label. But for agent delegation, who should handle this work in this context, it's different. The overlap is normal there because we have multiple agents that can solve the tasks as well, considering, for example, the GUI agent. And the choice includes also cost, latency, or the user experience that we want to provide to the user, in this case, in the driver's seat, for example, or the passenger. And here's an example where, for example, the ambiguity comes. Like if the user says, play some jazz, the media API may be the best if we have an empty screen, but if there's already a song or a playlist on the screen, then we can also tapping it. That could be also a valid choice. So the ground truth doesn't have to be just one label. We can have multiple acceptable valid choices. And basically, the point is also that the overlap is real, but this is not the only problem that we have in agent delegation. Even when it's implemented as a tool call, agents are not tools. a tool call is bounded, and the agent delegation is unbounded. So basically, delegating to an agent can start an autonomous loop. It may reason, ask for clarification, get stuck, resume later, or never return cleanly. So the orchestration is not just selecting capability, it's also deciding when it's safe and useful to let another loop take over, effectively unbounded control. So we have to distinguish between this, and then also with the overlap, there's the ambiguity. So here are some examples where, for example, it's clear. If I say, navigate me to Munich, this is navigation agent. But for example, the play some jazz, there are multiple valid trajectories, multiple valid agents that could solve the problem. So a reliable system should not basically force it into one canonical label. And it should use the runtime context and adapt accordingly. So basically, it's about the overlapping agents becoming multiple valid choices. And then it also leads to consequences in the evaluation. How do we want to do evaluation? And the benchmark basically should only ask whether the final task succeeded. No, it's also about the reasonable path, the cost, the latency, the user experience that we want to provide. And then we can accordingly create the data set that then have also the full runtime context. And then we have the metric. For example, sometimes we can optimize for latency, sometimes we can optimize for the human-machine collaboration. And after all, it's about also how do we want to build this multi-agent system in an enterprise. So how I would say, like in an enterprise, every team who owns an agent could build their own benchmark. And then after all, multiple teams can put the benchmarks together. And then we can build a shared benchmark where we also consider collaboration, coordination patterns, and basically how everything works together in the orchestration and delegation benchmark. So the patterns are just the means to connect the pieces of the multi-agent system. What matters is making orchestration, paths, and delegation decisions measurable, context-aware, and reliable. So keep asking, who handles this work? What path should they take together? And how do we know it was good? Thank you.
Okay, then we will move on to our next speaker, Nayaki Nayar, CEO of Sentiment Proof, transforming from SaaS to an agentic enterprise.
Hello, everyone. Good afternoon. Can you all hear me in the back? I'm not going up on the stage. I hurt my knee, so I'm not going to risk climbing up the stairs. So I just want to make sure everyone can hear me. OK, Nayaki Nayar. I'm the CEO of Sentiment Proof. You know, the topic I was going to cover today in the next 5 minutes is how we, as Sentiment Proof, who have been in the industry for over 20+ years, transform from a traditional SaaS business into what we call the agentic enterprise, especially in the world of content intelligence. If you take a step back and look at what's really happening around us, we live in an AI-driven world with infinite content. And when I say content, you have web content, mobile content, social content, documents, all kinds of content that large, big, global enterprises struggle with. We have over 5,500 customers worldwide across Global 2000, Fortune 500 companies, across financial institutions, healthcare, public sector, all kinds of various industries. And one of the key challenges that every customer that we talk to has is to make sure that content is compliant. And when we say content is compliant, content is accessible, especially with EAA, European Accessibility Act in Europe. In North America, we have what we call ADA, American Disability Act, requires every large enterprise to make sure their content is compliant. In addition to that problem, compliance problem, customers are also struggling with what we call content visibility. You know, in today's day and age, where search has evolved beyond the traditional searches into the AI-driven searches. Raise of hands, how many of you use all the other AI-driven searches for finding all your content, finding all your information you're looking for? I'm sure, right? Pretty much. This is the Agentic conference, so I'm sure all of you are using AI-driven searches. And the next problem is, you know, in this world, when everyone is a developer, when everyone can build content, when everyone can design content, how do you ensure that content is compliant and is performing? So our response, and I'll go through all the various agentic use cases we built, is to shift left, is to address this problem at the time of creation. As developers, as designers, as content creators are creating the content, are building apps, are generating more and more designs to be able to detect those issues up front during the creation and remediate those issues. Which is why last year we released what we call our Agentic Content Intelligence Platform across 4 key pillars. Across accessibility agents to be able to detect issues and auto-remediate those accessibility issues at the time of creation. Conversational analytics agents to be able to, you can ask any question, it'll automatically generate your reports and dashboards. Search agents to make sure your content can be visible in all those AI-driven searches. And content strategy agents for you to make sure you can do content briefs, content drafts, and all kinds of content descriptions there. And we also released what we call MCP server for us to be able to integrate agent-to-agent integration across all these AI-driven tools, across Lovables of the world, Copilots of the world, VS Codes of the world. And that has really transformed how we bring integrations to the market, which used to take maybe I would say weeks or months sometimes, can now be done in days or even minutes. So let me do a very quick, this is a recording of a demo that we captured, just so that you can see how easy it is for us to do these integrations. This is with the Lovable app that we integrated. And just asking, okay, what agents it has access to. And it immediately detects the various SiteImprove agents and Lovable agents and also the browser agents. And say, okay, what can you do with the SiteImprove agents? It'll highlight the various agentic capabilities we have, our alpha detect agent, our AI rules agent, our auto remediation agents. And as I'm running this in live, right? So now let's grab the URL of this website that you see on the right-hand side and do a quick check, quick accessibility check. And when I run that check, you can see it has highlighted approximately 5 issues there. Okay, now let me do a quick prompt for agents to work with each other. Our SiteImprove agents to work with Lovable agents to be able to quickly detect what those issues are and auto-remediate those issues. You know, you can see it's calling the agents through our MCP server and detecting what issues it has, and it automatically remediates those issues. This, ladies and gentlemen, used to take us anywhere from weeks to months to detect these issues and auto-remediate those issues. Now you can see it can pretty much be done in minutes. That's what we mean is to help our customers, all the content that they have, this infinite volume of content that they have, is to keep that content compliant and performing. It's not an either-or solution for us, it's an and solution, and that's all running on one single platform. With that, thank you all.
All right, we now have Surbi Rathore. Pardon me for not having your speak on Agentic AI is a UX problem disguised as a technology breakthrough.
Hey everyone, hope you're having a good time. We have spent the last day and majority of the day today talking about how are we building agents in the best way, monitoring them, orchestrating them, evolving them, but I'm going to spend the next 5 minutes giving you a little different perspective on like the reason why we're building all these agents is that consumers trust them to use and operate. And a lot of this is a UX problem and not a technology and model problem. I am the VP of AI products in a company called Invoca. We build marketing and revenue agents for brands which operate in highly considered purchases. Before I joined Invoca last year, I was the former CEO co-founder of a company called Symbol.ai for 7 years. Our company was acquired last year, and we spent 7 years on the infrastructure bed. We ourselves spent like a lot of money and time training language models, which were very specific to understand the nuances of human-to-human interactions. And of course, like my hypothesis has massively evolved over the last 1.5 years or 1 year since deploying these agents and using the models have somewhat become interchangeable. But really what matters is how does the design of these models and the experience with the consumer will dictate whether whatever you build the agent that was capable of performing the workflow actually influenced in the right moment with the right timing. So just to give a little background and the type of persona I'm talking about today, Invoca operates in an industry called considered purchases, where we work with companies with healthcare, telco, insurance, home services, where the consumer almost every time needs to speak to a human before making a purchase decision. These are not things that you operate on a day-to-day basis. And in these industries, earning trust almost needs to be instant. And agents that operate in these industries have to emulate the human trust that the consumers have been working for years with these brands almost immediately through the way that they are interacting with the consumer. The big problem here is not really to define workflows and do revenue operations or do agentic commerce. The bigger workflow is to actually win the user trust that is arriving when they're interacting with the agents with an already failed mindset. Like your users and the consumers that we work with day in and day out are so skeptical of interacting with AI agents. And that's not because of like their paranoia about AI. It's really because of years of gaps in technology that we have all been through and failed UX of the agentic experiences or conversational AI experiences that have been operating for a long time. So when your user starts operating with these systems, they're thinking that, oh, I'll have to repeat all the information. This agent doesn't know anything about me, and I'm just going to say, talk to a human and just get rid of this loop very fast. So that's why the hardest design problem isn't making the agent capable. It's actually making it trustworthy to someone that's walked in expecting it to fail. So we've built, to solve these problems, we have started to build like a context layer that specifically informs the UX. Invoca has operated over the last, I think, 14 years, and they contain huge volumes of call information, buyer journey data, interaction data, and all that we are mining to inform the knowledge and the training of the agents to inform what intents they operate, what actions they take, and that's all great. But we're building another layer that just informs the UX of the agent itself, and it sort of falls into 3 categories. One is, of course, like, what do you know about the consumer before the consumer even types the word, which is the context-fed UX. The second is the graduated agency, where at the time where you're designing the agent, you're really giving the agent the things that it should do and it should not do, and designing the experience for it. And the third is the in-moment reading, which is actually one of the most important things, because if you feel that there is urgency or something off the happy path that a consumer is facing with, how do you skip the usual normal path and design a workflow that gets the consumer a delightful experience in that moment? So these are just examples, and I'm going to go through quickly because of time here. But this is an oncology example, a patient trying to book an appointment 2:15 after detecting cancer and not available in the form fill. And instead of taking them through a painful experience of filling a form, the agent quickly books an appointment and confirms availability of doctors for that. The second one is around prescription refills, where the hospital has implemented a new MyChart system. They want the self-serve experience, but again, the timing after 6 p.m., trying to get a refill in place, left a voicemail, no response, and the agent quickly diverts them to the right experience to handle it quickly. The third one is just an example of how the same UX can be applied to support use cases, although we've spent a majority of time on revenue-generating use cases, where someone is operating in the morning, waiting for a video interview call in the morning, and internet is down. So how do you handle diagnosis, not through a 20-step process, but a 5-step self-diagnosis and stay with the call? So yeah, I just, because we're running short on time, but just leaving you with this thought that as you're all designing experiences for your agent, think about the user experience and really think about context being a key input to the design system for your agents. And if you don't have the data, collect it and build an agentic loop or connect to systems that actually power that data. Thank you so much.
We now welcome Daniel Fink, AI engineering lead at Cognizant, for scaling up config-driven multi-agent networks with Neurosan.
Thanks, everybody. Let's see. A little bit about where I come from. I'm from Cognizant AI Lab. We are a big R, little d, small group of maybe 30, 40 people or so, centered in San Francisco. We got some people in Bangalore. There's my people. And what I generally do is I take the research problems that are promising and then push them out so that they can be scaled up. And the greatest example of this is like 2.5 years ago, we were experimenting with multi-agent systems. And we quickly realized that the glue code of agents calling other agents was the noise in what we were really trying to do. And so we wanted to lift that up. And what we came up with is now known as Neurosan. And Neurosan is basically a configuration-driven system where agents can call other agents can call coded tools can call back into the agent system, and all of this is described in JSON, basically, except of course for the coded tool aspect. Every node can, in the system, describes upward to its upchain callers, what it can do, what it needs in order to operate in terms of information, who it can talk to, and then of course there's the system prompts overall. And one of the bits of secret sauce about what's going on is that the ultimate upchain is the user, and when it comes to secure credentials and stuff like that, we have a side channel of data which we call slide data, which allows you to put in the tokens that you never want to get in the chat stream, basically. So I'm going to focus on the last two bits here. So early on, we actually figured out that we don't really need to wait for the next great model in order to boost our capability. The real win is breaking your problems down so that a smaller model can handle it and handle it more reliably and more cheaply, for that matter. And the other interesting thing was that when given the right tools, we had all kinds of people starting to make multi-agent systems. Even our marketing people had some really great ideas and tools that they still use today. So some of the really interesting things that come from the configuration-driven aspect of these multi-agent systems. I'll start with the second one first, agentic webs. So if you develop a multi-agent system, it's actually pretty easy for that multi-agent system to then call out to another multi-agent system as a tool ad infinitum. We can call MCP servers, A2A servers, whatever other agent system you want, we could do that. Other interesting thing is that the common tooling for actually calling our agents in the first place, even with the secrets, is, since that's all standardized, the testing itself becomes data-driven in and of itself. This is the interaction that I want to have. That becomes data-driven. And then it gets even crazier because now, because we have, it's the JSON files or HOCON files that describes these agentic systems, they're just forms to fill in. So we now have multi-agent systems that are basically vibe coding other multi-agent systems. And they can call them as a thought. They can, as a perishable thought. They can then be downloaded and used as part of the overall system. There's some other stuff on there I'm going to glaze over. So how can we apply this stuff? It sounds kind of fancy. What we're seeing here is in the center is what we call the front man. He's basically the root of the system. And he is calling out to other agents that are kind of middle tier, and then in the center circle, and then in the outer circle is are the actual leaf node agents that are actually doing something. So the example here is a corporate internet. So think of your corporate homepage that you probably look at least once a week, if not more. And different departments, HR, finance, IT, they all have different needs. They all have different agents that actually everybody kind of needs to kind of needs to be able to access. And so what we do, how do I go back? Here we go. So we have this prompting infrastructure that's called AOSA, and the idea is that the guy who is answering the current question, he doesn't know anything, but he knows who else to call, and that all contributes down, trickles down, so that different aspects of the same question can be answered by HR, by legal, yada yada yada. So the coordinator doesn't know anything, but the people down below do, and then as information comes up, there is an aggregation of knowledge that happens on the way up. So we actually convinced our corporate IT department to help us eat our own dog food. And currently, they have about 200 leaf-level agents coordinated by this AOSA infrastructure. Everything from ServiceNow, Salesforce, PeopleSoft, all the stuff that people know and love. It scales up ridiculously, which we're very happy about. And the results are basically in the ticket counts. So the blue line that starts in the kind of upper left of that graph and kind of goes to the middle left of that graph is the ticket count. And the blue vertical line in the center there is kind of when things were deployed, actually a little bit to the left. And when we deployed that, we basically found we had about 30% drop in overall tickets because the agent system was handling requests better than people overall. I just want to say that this stuff is freely available. It's agreeably licensed. We encourage you to try it out for yourselves. And we look forward to actually working with the AIF to make this happily available in the Linux Foundation. And we're going to have a site, bring your own key site, which this whole system supports, where you can vibe code your own multi-agent systems. Thank you very much.
That now brings us to the session for agent evolution and benchmarks. We'll be starting with Debarshi Raha, VP and fellow engineer at DigitalOcean, on preferences, benchmarks, model routing, and how teams actually build.
Okay. Are you able to hear me? Okay, cool. So I am Debarshi. I will describe how to build an routing system for the models, for the agents that you need. So before that, quickly about me. I am a fellow engineer at DigitalOcean. I joined DigitalOcean almost a year back. I am working on data and AI stuff. Before this, I was a long time at AWS. I was working on launching fundamental services like OpenSearch and several AI/ML services from ground up. So now a little bit about DigitalOcean. So DigitalOcean is a cloud native, AI native, full stack cloud service. You can get everything from the bottom layer, which is infrastructure, from compute to storage to networking to up the stack, data and learning to manage agents. And the inference router is sitting in the middle inference layer, if you see, and it is actually going to impact everything on top of it. So since we launched the inference service, we have onboarded 70+ models, including the recently leaderboard topping Kimi K3 and Opus 5, Cloud Opus 5. And those are amazing models. I love them. But there is one problem, which is cost. So if you are paying for every task going to the frontier model, then there is huge cost. And every company is kind of feeling that. If you see Uber kind of exhausted their whole year of agentic AI budget just within 4 months. Similarly, Walmart is trying to cap on the AI stuff. So every company is feeling that, and the top reason for that is the second one, which is fit. That you do not need a frontier model to serve every single of the requests. You can always look at like using a smaller model or a medium model for some of the other tasks. So that way you don't have to pay the frontier cost for every model. So that is the fundamental problem that we are facing, and we are seeing this challenge from all of our customers. And there is an operational problem as well, which is a risk. So if you depend on just one model, then you are risking your whole application if that one model goes down or if it degrades. So all these problems together, all our customers come to us that, hey, how can we reduce our inference bill? This is not cheap, and everyone is investing on that one, but everyone wants to reduce the amount. Now let's see how we can do that. So what actually needs your frontier model capability? So if you are just doing a classification or labeling problem, you do not really need that. You can use a simple model, a small model to do that. If you are doing, say, writing task or summarization task or translation task, a simple, small to medium model will be fine, just fine for that. Or if you're doing code generation and all, maybe a medium model is fine. Or if you're doing scientific reasoning, the reasoning kind of stuff that really needs the depth and the power of that frontier model, like medical things or maybe security analysis. For those things, sure, you want to use the frontier model. That's the reason. So we see that there's huge opportunity here that if you can direct to some other models and take the support of other models instead of frontier model for everything, then you have huge opportunity to reduce your cost. And that's the reason we launched the inference router, which sits in the middle of your client and the server. So you do not need to statically code that, hey, which model you can choose for which of the tasks, or you do not need to build it yourself. So we have launched the inference router that is sitting on the server side, and you just define that for which task, which class of task you want to use which model, and then we are going to intelligently route it to that model with all the real-time feedback, like what is the latency currently, what is the model available, what is the cost. So with all that real-time metrics input, the router in the middle will decide and appropriately route to the right model. So some of the benefits that we are seeing already in the industry. So we have this customer, Lavo, which is a Canadian law-based AI startup. So you can go there for legal advice. You can subscribe, and if you have a legal question or something, you can go there, and they will give using AI as well as based on the human in the loop. Now, they are seeing 40 to 50% reduction in inference cost. So similarly, we have seen you can actually go up to probably 80% of the cost you can remove, you can reduce by using this router. So that's why we are super excited to launch this and work with our customers to reduce their cost, reduce their utilization, model cost and bill without losing the capability and the quality of the model and the task output. How much? Okay. So that's why this is becoming the most important part of the stack. This is the latest FinOps. So I was at AWS before this, and I have seen how long it took for the cloud cost optimization to be a real discipline. We were really putting a lot of effort in during the COVID time to reduce the cost, optimize the cost. But here it is happening right now as we speak. It is not waiting. So within 1 or 2 years, I have seen massive shift here. So now let's get the intuition of what you need to build a model router service. What actually you are looking for? You have a task, and you have a lot of prompts and other things with it. In addition to that, you also need to consider the cost that you are willing to spend, the latency that your application can take. So all those are dynamic things. Those are not static. What is the latency? What is the cost? And those things. Plus, of course, the prompt and tool and a lot of things, those are there. Now, all these things combined, your inference router should be capable of routing based on those. Now, those no public leaderboard or public benchmark tell you. So you need to encode those in the router so that it is not based on just the benchmark, that, hey, this model is best for this task, so you're blindly routing to that. So you encode all of those and real-time, intelligently route to that. So now this is how we built it. So in the middle, you can see that there's a Plano, and there's a routing model on the top. So this routing model is a purpose-built routing model just by us, and all of this, Plano and the routing model, both are open source that we are talking about. So there is no vendor lock-in here. You can use it yourself or host it or even contribute it. So that will be awesome. But the routing model is a 30 billion parameter model that is purpose-built just for this task. And as it is purpose-built and trained only for this routing task, it beats the frontier model benchmark just on the routing task. Like GPT-5 series model and all, like it has beaten on that one. So the Plano, so all your result, all your question comes to Plano, and Plano is a proxy in the middle. The proxy will route it to the router, and it will get the result, and then it will rank. So if you remember, I talked about, hey, what is the latency you can tolerate? What is the cost you are willing to spend? So based on cost and latency, it will re-rank the models. That for this task, you have a candidate set of models, it will re-rank. So that is totally dynamic. So the Plano supports the observability from multiple systems. Of course, like here, it is plugged into DigitalOcean inference system. So you can plug into any of your system that you want. So with that, it can get those real-time metrics, and it will re-rank and route based on that. Now, this is how we think it should be built. Now, there are, of course, other ways to build it. Like, for example, you can do it statically. Like, on your home page, you can have, hey, for summarization, this is a button, and that button is always going to this model. Or maybe you can have coding or translation. For translation, you are always sending to this model. Now, those are super static, and you have to keep updating your client side. Or in the client side, maybe you can use some other LLM to decide the routing. But then you are paying double the tax, right? You are increasing the latency by around 600 milliseconds or so. In addition, you are also paying more. So you double the tax just to use another frontier model for routing. And here, this is free. There's no extra cost. There is no additional cost, and latency is only 200 milliseconds or less based on the task. So that's why we believe a purpose-built system just for this task is best suited for router. And this sits on the server side. This is not on the client side, so you don't need to change client all the time. Hey, now there's a new model, or now there is a new task that I want to classify or I want to route. So you don't need to keep changing your client side. You just come on the server side. It is configuration. You just tell on a natural language what you need. I'll show you a demo, then probably it will be more clearer. So this is the system that we have built, and we have open sourced it. So you guys can put your hand on it and just try to use it, improve it. Would love that. So this is a little bit about how we are operationalizing this. So you decide your rules in natural language. And on top of that, there are some presets. So using public benchmark and using task-specific benchmark, we have decided which model to go, what are the candidate models for a task that is best suited. So you can start with that preset, and you can, of course, change it as you go. So that and also you plug in your evaluation. So we also have the evaluation framework. So you use the data set that is needed for your company, for your task, not someone else's public leaderboard. So you plug in that eval and make sure that the router is working fine on that data set. If not, then you come back, you adjust, and then you have the loop to make it fine-tuned for working on your system better. So I talked about preference over router. What I mean by that is you decide your preference, that this is the latency you can tolerate, this is the cost you want. And based on that, the router routes it. Now, there's a cache over routing part that I have not discussed. I'm running low on time, so quickly let me tell. So cache over routing, you must consider, because if suddenly on the, let's imagine an agentic system, when you are writing code and it is automatically discovering code, analyzing code, writing code. So all of those, there are a lot of prompts that are same on that agent system. In every loop, there is a same prompt. Now, if you suddenly, in the middle of the session, if you suddenly change the model, then you're going to lose the warm cache that the model was already having. So you don't want to have that. So you want to have the cache over routing. This is something we are doing right now. Watch it decide live. So I wanted to show a demo. I don't know how much time I have. Maybe 2.5 minutes. OK, let me quickly try that. So this will make it like something like very concrete for you. So you come to DigitalOcean, you just click on create router, you just give a name. Let me give a name quickly, test, some description. Now this is where you add task. And I'm just, for the sake of time, I'm adding a preset task, let's say summarization, and save it, that's all. Now let's see if the Wi-Fi will work. I do not see it is saving. So I don't think the Wi-Fi is working. But anyways, what happens is that, so you see there are all these tasks. So for each of the tasks, there is a set of models. You cannot tune the model. And you can then decide you want to rank by cost or latency or that kind of thing. So when the Wi-Fi was working, now there is a playground. Just with one click, the router will be launched immediately. And with one click, you can launch it in the playground and compare with another model, like let's say Opus 5. And just before this, I was trying it out. So if you run the router versus the Opus 5, so router was around, I think, 20 times cheaper or so than Opus 5. And it also completed the task around 67% faster. So that was the result. I wish I would have loved to show that, but it is not working. But anyways, let me come back to this one. So now just going to summarize some quick facts. So as I mentioned, the router is the model is a purpose-built model. It is only 200 millisecond or less latency it will add on the server side. It is a 30 billion purpose-built model. It is zero application code change as you need. That I told, yeah. And it is free. It is completely free. So there is no, you're not paying any double tax. So if you're using an LLM, as I mentioned, you have to pay double tax for both the latency and the cost. There is no double tax on it. It is completely free to use on DigitalOcean, or you can also host it on yourself. Now, just to summarize everything, so I mentioned about eval, that you have to plug in the eval on that so that you know that it is working fine on your data set. And of course, there is a caching is a very big thing that I told. And personalization, this is, I am super excited. I myself have launched a personalization service before. And here, what I mean by personalization is the more you use the router and the inference, the better it becomes. Because if you enable the log and traces, then all those feedback in the continuous loop and check on the eval, and it continuously improves. So that is awesome. Without doing anything, you're not building anything on your side. Without doing anything, the router is improving. So that's where I want to leave you. Maybe. So this is something we are working on. Maybe next time we can do a deep dive on that one. With that, that's all. So please use it. Try scan the QR code if you want to use it. Come to DigitalOcean router and just see how it helps you to reduce the cost. I think this is a fantastic feature you all should be thinking about. And yeah, come meet me after the session if you have any questions. Thank you so much.
We now have Emily Zhu, with Head of Enterprise AI at Scale AI, on the exam before enterprise deployment.
Thanks for the intro. Currently I'm working at Scale AI, had the AI functionality within enterprise. I really enjoyed the opportunity to talk to many of the enterprise customers. Before Scale AI, I spent 11 years at Google. I'm a core member of the Gemini team. In addition to contributing to Gemini development, the most relevant experience I have is I built a team to do the cloud agent benchmark for Gemini. So part of this talk really kind of capture a lot of the observations and reflections I have with these different two roles. And the talk is about the exam before the enterprise deployment. Forward. OK. So at this moment, we're all from AI communities. And there's one thing we all know. The value of AI will have to land to produce productivities for our real economics impact. And that is not going to be happening if AI stays in the demo and the pilot. We need to have all the AIs to be deployed from pilot into production. And so this talk is really about how we get there from pilot to production. What is the gating decisions people need to make? And the question really is, can this agent be reliably deployed to do useful work inside of our organization? So things we talk about benchmark, and then we just start with benchmarks. Right now, I don't know how many benchmarks you are actually aware of, how many benchmarks are out there, right? There's hundreds of benchmarks out there. But if you look at those benchmarks, and we use that all the time, one thing you actually would realize is they really measure a ceiling. It measures the gap between what the model is able to do right now and the top of the human intelligence, right? And then when you if you're a benchmark developer, when your benchmark have a lower score, you feel pretty excited because your benchmark is facing developers, model developers as your customer. When they see a lower score on the benchmark, they feel there's a gap, there's room, there's things they need to do. They feel very excited about it. But if you bring the same benchmark to enterprise buyers, they have a completely different view. And I can share an anecdote with you guys. So when you talk to an enterprise customer, we have actually a particular use case, text to SQL. The executives, they don't understand why your agent will not be able to actually get 99% of the reliability, given everybody saying agents so smart now. And then the researcher is going to show them all text to SQL benchmarks. I don't know whether you guys know what's the top of the text to SQL benchmark. They're only 60%, 70%, because people don't wish their benchmark to get saturated. When the benchmark is saturated, people don't use it anymore. But the reality is for enterprises, they really want to see that number, how to get that number into 95, 99%. So that is actually a totally different mindset of things. So this is what we say the gap is, where the current benchmark really measure the capability. You see a score, you rank all the models, and the model compete on it. It's really developer facing. But what I actually need for enterprise adoption is the deployment readiness. Is say, is this use case ready for deploy? What it takes for it to deploy. And this is what we're going to talk about. All right. OK. So before that, we'll just go through 5 very basic questions that enterprise buyers ask. The first one is, what is ready for production today? We have a list of priorities. But among all of this, which is hard, which is relatively ready for me to deploy? And the second thing is, how can I actually measure readiness? Because readiness is a concept. How can I quantify it? And how can I trust the outcome? But more importantly, if there is a gap, if it's not 99%, let's say it's 90%, doesn't matter how it's measured, we'll cover that later. How can I actually fill the gap of the 10%? Because I can't go with 90% for production. I always need 99 point reliability for my product to be deployed to facing the customer. What should I do to fill the gap? And it's actually not surprising because right now there's always the human oversight. And the question is, what is the human oversight policy that I can use in order to get in there? And there's also a question about the cost because if you have agent, you have tokens on this side, and now you also have human on the other side. Adds up together, am I actually saving money from the AI initiative? Okay, so overall, the readiness profile really talks about how can we do qualification? What's the risk envelope? What's the oversight policy? And what is the improvement path to get from where we are to what we want to be? Okay, so now let's get a little bit more concrete. From the questions, how could we actually get evaluation primitives? Okay, so the first one is, can we trust the answers? So one agent produces an answer for us. What would be the evaluation primitives that allows us to actually evaluate the answer trustworthiness? I think this is no secret. Essentially, it is grounding, how we actually measure the citation precision. For every answer, for every piece of information in the answer, is it grounded into a source piece of information? Do we actually cover everything within our evidence database to produce? Do we miss anything? The recall problem. The next one, couldn't actually see this very well, is the policy compliance problem. A lot of the cases, the agents give you a right answer. But the question is, does it follow my internal policy? I'll give you a very concrete example. In working with one of the healthcare customers, they would like us to actually do a quality auditing for clinical safety events. The safety event would say, can we identify clinical acute kidney failure accurately? And in order to identify that, they basically say you have to look at the labs. You have to look at the increase of creatinine in the lab measurement to get it. But when we deploy our agent, we see the agent is becoming smart. It does a shortcut. What it does is instead of retrieval the creatinine measures from the lab measurement, what it does is it actually just look at the clinical notes, look at the diagnosis notes within the electronic microsystem to say whether this person has acute kidney failure. So it doesn't really follow the policy that is specified the clinical environment to do the job. And that's actually a problem we need to address. Then the third question, my favorite question, is does the agent know what it doesn't know? This is actually super important, and two things related with it. One is the confidence calibration. A lot of cases, the agent would say, I'm confident 60% of the time, right? But is it really? Then you really need to calibrate the confidence that's self-claimed by the agent to the reality. Is it really 60% of the time it is producing the right answer? That's a calibration question. But more importantly is, if it doesn't know, we need to give them a policy to see when you should stop giving out answers. You need to abstain. You should say, hey, I need human advice. I need to pass it over. So this is the third thing that we need to evaluate to answer the question. Okay, I have 2 minutes, but I'll be fast. The right operations. This is where the agent system we develop interact with the traditional enterprise system. Because when you have your agent system, it's not just about the security reliability of your system. It's when the operations from your agent is actually getting to enterprise system. How do you manipulate? How do you mutate the state of your enterprise system? Is it recoverable? Is it a rollback policy there? And the last one is the oversight economics. And this is what we're talking about. If you have human oversight there, in combination, is the economics actually makes sense. Okay, so, all right. Putting the primitive into a framework that how we actually organize evaluation primitives into a thought framework. So this is kind of a surface we're using in our upcoming benchmark coming up this month. The first one is we actually think about the surface where the agent is interacting with the agent system is interacting with the enterprise system. The first one is inside. We just get information for human review. And the policy is really about human review policy. What you do is you get the rate operations, and you want to see whether the question we want to verify is whether the answer is trustworthy. The second surface is actually your agent system is interacting with your enterprise system. The question is whether you change it in a way that is recoverable, trustworthy. Are you actually doing it in a privacy-preserving way without leaking your information? Do you do it in a way that you permutate, you mutate your system in a trustworthy way so that's recoverable? The last one is, we're getting there really fast. So the last one is open conversation. It's not just interacting with your enterprise system, but interact with your enterprise customers in the open conversation way. In this environment, the input is from open space end users. They could give you malicious, misspecified information. How do you actually steer the conversation to achieve your goal? So that's the three kind of vulnerability or evaluation services. So with that being said, the deployment profile really answers a list of questions. 7 of them, I'm not going to repeat them, just read off the slides. I want to respect the time and then just really go to the final 2 slides. Really, 2 things I want to call out here is in enterprise benchmark, what people really want is not a number to say what's the score of it. What they would like to do is to have is really 2 things. The first thing is this use case ready? But meanwhile, what they actually want to understand is what is the economics? What's the cost I need to pay to form a human oversight policy so that I could achieve my reliability right there? And the path to improvement is not a score improvement. It's not say I'm having the score from 60% to 80%, 90%. The path for improvement is economical change in the sense that initially you need a heavy human oversight. But over the time, with the improvement model quality, it's actually the cost you pay for this task is reducing. We are constrained by reliability. Reliability is not something you can trade off. What is trade off is what the policy needs to be there, how human and agents can work together in a trustworthy way. And this is my last slide. Don't only ask how intelligent the agent is, ask what it's ready to do, under what constraint, and what's the risk and what's the cost. And that's how I hope I'm right on time. Thank you.
Now we have Chengguan Wang, Assistant Professor, University of California, Santa Cruz, a research advisor for Scale AI, from training to evaluation, open recipes for building agentic AI at Scale AI.
Hello, everyone. My name is Chengguan Wang. I'm currently assistant professor at UCSC, and in the meantime, I'm also, I think, working with Emily also closely at Scale AI as a research advisor. So today I'm going to talk about basically the post-training to evaluation, what we'll be working on, right? Try to build a frontier, hopefully, agents, using what we have already at Scale AI. Let's get started. So I think I can spend a little bit time on talking about, if you guys don't know Scale AI, right? So the mission of the company is really just try to build reliable AI systems. I think for the world's most important decisions, I think it's founded by Alex in 2016, and it's pretty big right now with many employees and the offices across, I think, US and also in, I think, other countries as well. But I will get straight to this topic. I think I will mainly cover, I think, mainly two topics. One is the post-training, right, as part of in the title, briefly, but only briefly, because we only have 10 minutes. I think the second part will be talking about evaluation, and I try to bring some synergy between those two components, right? So I will start just with a general idea about the current research focus at the Scale on the post-training part, which is trying to, right, so like a research training is also like this, right, moving from RLHF to Rubix-based RL, right? So I think this is a practice we got from, basically working with the frontier labs to providing the data services, and we figure out this is something really important for post-training. So there's definitely challenges over there, right? How to really design effective reward and how to use that reward with RL and how to make a reward even better during the training, during the RL phase, right? So we have been publishing, I think, at iClear this year, SML, I think hopefully we get something also at the NeurIPS so on so first, in the middle of the response. But we are able to, I think, push a boundary of GRPO, right, by using a Rubix-based reward paradigm, right, just basically improve the performance, and is able to, I think, also gather some, I think, interesting receipt or, basically insights, I think, from the process of training and also working with the data, how to basically play with this flywheel, right, the data and RL part. Hopefully I can get something, for the takeaway for you guys today, right? So the first thing I want to focus on is really this RL recipe. We actually realize it's important. I really want to highlight or avocado this is basically the Rubix-based reward, right? So this is important because I think in general, right, so if we want to make RL work, right, so previously I think the training is on the so-called variable domain, right, where you can pretty much know, for example, coding or math, you can pretty much know whether this is true or false, right? You pretty much get a ground truth verification, right? But in many real-world cases, where we really care about, or frontier lab really care about, is really you want to make this work for domains where there's no verifier, right? Whereas it's not a verifiable domain. So we need to find out a way to make it work for those open-ended domain. Could be science, could be something else, right? Could be for our personal tasks. So we are trying to basically set up this paradigm where we ask, right, basically a criterion or evaluation criterion that turn that, into verification, right? Something like that. So we are able to really, I think, build a new reward model which is not basically distinguish a better response, versus a worse response. We are trying to say which one is better and is ranking based from Rubik's. So it can scale up to real world scenarios. And we build a reliable pipeline like we show, I think in these two figures where we can start with something simple and gradually build a very high quality Rubik's and use that in RL phrase. And we witness improvements on open-ended tasks. Right, that's a takeaway. And then this is a natural extension of the first work, right? It's also on Rubik's, where you train a model, but the policy will change, right? Your policy becomes better, right? Better code, right? So, but there's still something, is changing. So you have a reference policy, you have some current policy, and you figure out what is missing in the current reward and generate better Rubik's or online Rubik's where you can integrate this into the reward model, where then you can pretty much just train better and be more robust to downstream tasks. So this kind of online Rubik's, I think, evolution, I think aligns very closely with the recent trend in, I would say, self or improvement or recursive self-improvement line of work, right? We are moving towards there. And the second part, I think that's pretty much I just want to highlight a few research done the post-training. And I think in the evaluation space, I think it's definitely Scale's main focus is really basically driving those insights from the training and talking to the customer and then build some, I think the words, basically worldwide leaderboard for those frontier models to be on, right? So there's many going on, but I would just want to highlight a few projects recently, right? So many of you guys, definitely it's like a really working demo of agents, right? It's like survey agents or coding agents, right? I think Scale invests a lot in this domain, try to build a reliable benchmark to try to understand whether, what's the true capability of the agents, right, of survey agents. I think you guys know benchmarks such as Survey Bench Pro, where you can pretty much just think about the problem is like there's some text description about the problem in the GitHub, and you just need to ask the agent to generate a patch, which can eventually just fix whatever bug in the original repo, right? But I think in the real world, it's much messier, right? Where I think as an engineer, we are not only just looking at the PR and looking at the issues and generate basically response, right, as a patch. You need to deal with those writing a unit test sometimes. You need to even figure out the problem by just basically go back and forth, look at the repo, ask some question, and answer that question so we can figure out what to do next. So that would be some insight we can borrow very differently from working with benchmarks such as Survey Bench Pro. So we released this new benchmark called Survey Atlas, right? I think it's widely adopted by Frontier Labs right now. And other than Survey, another, I think, focus of the agent eval we are building is in this professional reasoning domain or this kind of AI for science domain. I think definitely, I don't need to say too much about HLE, which is like a professional reasoning benchmark. I think people are still trying to hill climbing, right? Try to become better from different like model families, right? And also, we are also working on this drug discovery bench, which is trying to really build some real-world healthcare environment where we just work with experts, generate this real-world basically drug discovery tasks where we start from the concept and then deliver the drug. We recently also released a preprint on that regard. And we are also working on tool use, right? So there is a debate on what is the best, I think, tool interface. Is this a CLI or is this MCP? I think we get interesting, I think, conclusion. Just high-levelly, we find out once a model becomes really capable, like a recent Cloud 4.8 or GPT 5.5 or 5.6, that doesn't matter. So model will learn to use the best tool interface possibly, right, in a real-world scenario. So that really doesn't matter unless you basically you give the same backend tool, right? that the interface really doesn't matter. And we're also working on this computer use agents, right? We are trying to benchmark computer use agents. So we are trying to scale up the computer use agents environment benchmark because each of the computer use agent benchmark is really very expensive to run, right? It's a multi-model, and there's many, I think, details you need to consider in terms of verifications. So we think about a way to actually, based on some existing high-quality benchmark, and really just generate long horizon, more challenging, more real-world tasks from, based on those existing benchmarks. I think we show that we can pretty much bring down the performance of the original OS world, where I think the state of art of this, I think Opus new version is something definitely beyond 80%, bring it down to something 30%. So there's a way we can construct real-world data sets synthetically, but in a very high-quality way. This is pretty much what I want to just final slides, technical slides, where we can pretty much build a synergy between evaluation and post-training, right? Just draw insights from post-training and try to build better RL environments, and also draw insights from evaluation failure mode and try to build better post-training algorithms. Hopefully this can run forever, so we got those better eval and better training result as well. So just closing, I think Scale is working with many different frontier labs, governments, and also enterprise and robotics, right, on this physical AI. And another advertisement, I think we got this third edition of the Agents in the Wild workshop accepted at NeurIPS, right? The deadline is coming soon in the end of this month. I'm one of the core organizers there, so we have a wonderful panel of speakers, panelists. Don is there, Joshua is there, Java is there. So feel free to submit and see you guys at Sydney. Yeah, that's it. Thank you.
Next we have Jaylin Wan, PhD, Senior AI Engineer at Postman on measuring API agent reliability for long horizon tasks in production.
Hi, this is Jaylin Wan. I'm an AI engineer from Postman. So today I'm going to present our benchmark called API Flow Bench. So for enterprise, when a company, they use the AI agent to do a long horizon task, they're already facing an issue that a small mistake made by AI agent at the early stage can cause the whole task fail. And then when engineer build a product for the service, people are usually doing the task like connecting the building job to a monitoring API, right? And also like creating a record or recover from the rate limit. So our bench that included those kind of tasks to evaluate the models. And so what we found is on the single API task, most of the model, even the live model, they are very good at the performance. They can reach like 88% and 97%. So that looks the problem solved. But the thing is, when we connect those single tasks together into a long dependent chain task, then the score dropped to 44%, 73%. So the task itself didn't get harder. But if the later task is depend on the results of the previous task, the earlier task, then that's where the model starts to fail. So in an enterprise, a lot of business logic is wrapped in API, and now we are wiring AI agent into those APIs. So a small error caused by AI can become a big problem in the later time. And nowadays, the real problem is not can the model answer in question. That's a chatbot. You guys all know it. And the real problem is can the AI agent stay correct across a long horizon of dependent chain tasks. So that's the difference between answering and executing. So we, let's go to next one. Okay. Okay, here is, so one or two failure mode is not enough. We want a minimum set that covers the real API works. So in our benchmark, we break the API works into 7 failure mode. authentication, discovery, schema repair, multi-step execution, error recovery, pagination, the statelessness. And we grade each of them separately because they're failing for different reasons. Like the statelessness, for example, the agent updates something at, say, step 3, and then step 15 only works if the agent saved the updates at step 3. So a model failing at statelessness has totally different reasons than failing at pagination. And we grade them differently so it can tell us why the model fails. Okay, we approximate real users' workflow with synthetic data. And we build a simulated enterprise API ecosystem, and that mimics the real company's API. And then we generate tasks on top of it. So here is our task generation pipeline. We start from the enterprise API ecosystem generation at the step 0. Then we follow those 9 steps to generate task one by one. And each generate task, we have a validation step. So we use the frontier model to try each task 10 times, and we only keep the task if it passed 3 times. So why we are doing that? Because when we use the language model to generate tasks, some tasks are just not solvable at all. So we don't want to generate a bunch of unsolvable tasks and then use those to evaluate frontier model and claim, oh, there's a limit of the models. So if a task fails the validation, we feed the trial transcript and the code to a fixer agent. And this fixer will fix the task, and we rerun those 10 trials again. And then if it keeps failing, we discard the whole new one and regenerate a new one. So that's how we make sure each task we generated are solvable and reasonable. So this bench is constructed by an API ecosystem, the task on top of it, one shared harness, and the grader that score each trials. So for the harness, we designed 7 tools. So they work on 5 different entities. So each task and every trial run on the same harness, but just with different ecosystem and different graders. So for the grader, we have 3 validators. So 2 are deterministic. One check the final state of the environment. One check the final answer the AI agent provided. So we use those 2 to grade each trials. So that's the pass rate you guys can see in our leaderboard. And we also use the language model validator. So that's not part of the score, but we use it to flag the doubtful pass so human can review it. So to make the generated task trustworthy, we designed 3 gates, and each gate kind of avoid different kind of failing during the task generation. So the first gate is called self-testing. A blank submission should always fail, and if we use the reference answer, but we substage the evidence, then this grade should always fail. Otherwise, there is a problem in the task or validator. And second gate is called solvability. So remember I mentioned we use the frontier model to try each task 10 times, and we only keep 3 passes tests. So that's how we make sure the tasks are solvable. And then third one is golden replay. So when we build a chain task, we put all the reference answer from each subtask together and then append them into this chain task and issue all pass. So that's how we make sure this formed final chain task is actually correct and it's working as what we want. So for the experiment, we run 467 tests across 13 general world. And eventually, we got 11 20-step long chain tasks in our bench. So we evaluated 19 models. We run 5 epochs for each model, each trial. So in total, we got around 44,000 trials. And all the transcripts are available in our leaderboard. You guys can check it online. We are planning to expand the number of tasks and also the length of the chain tasks in the next version. So here is the leaderboard results for these 20 chain tasks. So GPT 5.5 is on the top, and orange bars are the open source model, and purple bars are the closed models. We actually have this leaderboard updated this week, and we have Kimi K3 and the Fable 5 also included. You guys can check that online. So I would say, okay, I think I jumped a little bit, but it's fine. So an interesting finding that we found is right now at this time point, the open source model actually approaching the top group of the closed model. Like in our bench, the GLM, the Q1 3.7 plus also reached the second and third position. So let me see. Okay, here are 3 takeaways. First, I would say right now, all the live models, even the older models, even the live models, they are very good at single task. So they all got high pass rates in our solo task in our leaderboard. But so we cannot reveal the gap between them, and that's why we create this chain test to test their limit. So we saw the case a lot of, it happens a lot that a model made a small tiny mistake at the early stage, and then that tiny mistake becomes a broken report at the later task. So second, when you guys generate synthetic task, always use the hard gate to make sure the tasks you generated are trustworthy. So when I say hard gate, the example could be like turn times trial must has at least 3 passes. That's how I did. You guys can figure out more way. And also use the golden replay to make sure your reference answer is actually working. And the third one is both the deterministic validator and the language model validator are needed. So when you create a validator or grader, be sure to use human in the loop to keep polishing your generator, because a wrong validator cannot reveal the true performance of the models. Okay, here, that's all for this present. So the blog and leaderboard are all available at blog.postman.com. If you are interested in whether your API are agent ready, come talk to me after this session. Thank you.
And now we have Rahul Krishna, Senior Research Scientist at IBM Software Innovation Labs on ScarfBench. Can agents migrate enterprise Java?
All right, hi, hello everyone. I'm Rahul Krishna. I am a Senior Research Scientist at IBM Research. My talk today is going to be about enterprise Java applications and how effective agents are in migrating them from one framework to another and modernizing them. So enterprise Java is, applications in enterprise Java and modernization outlive the frameworks in which they're originally written. And it's a large, enterprise applications that are written in Java remain critical. Legacy applications were written in frameworks, and the applications themselves often outlive the frameworks. And modernization is an important use case because it's important for us to modernize the application into newer frameworks so that they have supported runtimes, better security, deployment modalities, among others. But the key insight of deployed applications is the institutional knowledge that have been embedded in the application over several decades. These include business rules, data semantics, workflows, and integrations. And migration must replace the underlying technology stack rather than while preserving the application behavior. Now, this is challenging because the Java frameworks with which many legacy Java applications are written hide the runtime behaviors with their APIs. So these means they use different proxies, reflections, interceptors, and the code itself doesn't really capture any of these, and these are taken care of by the framework themselves. And as a consequence, there is not really a one-to-one equivalence between an application written in, let's say, Spring to that written in Jakarta. And when we migrate these applications, it might seem like they build correctly and they run correctly, but there might be silent failures that will only show up at deployment time. Just to kind of ground this benchmark and why this is relevant, I wanted to show this slide here, which kind of lays out the architecture of a typical Java enterprise application. So large applications are usually organized in tiers, and each tier addresses a specific concern. Presentation layer, for example, presents the application to you through a browser or a phone application. And all the way down, we have data access layer, which does database reads and writes, and a cross-cutting concern, which ties them all together with configuration, security, and so on. But this is a really challenging problem because if you look at the application, a lot of these behaviors and the the business logic that's embedded in these applications are usually hidden behind framework and their APIs. And each framework have their own idiosyncrasies. For example, dependency injections, annotations, and so on in the application dictate how the business logic is embedded. And if we go hunting for it in the code, we may not find any of these. Even though these layers are separate in terms of their concerns, a deployed application has all of these layers interacting with one another, often at the same time. And therefore, this is a challenging problem. Now, in order to solve this, we built ScarfBench, which stands for Self-Contained Application Refactoring Benchmark. And the objective is twofold. First, we wanted to see how effective agents are in migrating applications and modernizing them from one framework to another. And second, in the process of doing this and understanding agent trajectories, we wanted to build a field manual of sorts on understanding how to build agentic solutions for general modernization. And we broke this benchmark down into two groups. I'll quickly go over them. So we have focused applications and whole applications. Focused applications are self-contained apps for a single layer that we just discussed, and whole applications puts them together into a cohesive business use case. This is just a high-level overview of the applications. So what we did at IBM is we had a lot of subject matter experts manually convert each of these applications that I've listed here across all of these frameworks through Spring, Quarkus, and Jakarta. And each row here is an application, and a unit of migration could be any app from one framework to another. And the objective of doing so is twofold. One, each migration has its own idiosyncrasies, and they're asymmetric in the sense that Spring to Quarkus is very different from Jakarta to Spring. And we also wanted to see how effective agents are in tackling independent layers. Agents might be really good at converting presentation layer, but they might struggle at the integration or data dependency injection layer. Like I mentioned, each of these layers are isolated, but a typical deployed application is a collection of all of these layers. And often these applications have all of them communicating with one another and interacting with one another. So the whole application part of our benchmark captures many of these applications, both as a monolith and equivalent deployment as a microservice, which again, subject matter experts manually converted across all of these frameworks. So at a glance, we have about 38 applications individually, but this translates to 114 variations of the same applications, and directed transformations add up to about 228. But the key distinction here is the handwritten test cases. So as we migrated each of these applications, the developers wrote test cases for the behaviors that they expect in the applications when they're deployed. And these test cases vary all the way from HTTP checks that I'll show in a second to see if the app is hosted in HTTP and HTTPS, all the way down to JSP pages to see if the deployed application, browser click actions, and the data is propagated correctly. So here's a simple smoke test, and there are many of these that I list, but this is a curl test that just ensures that the deployed app in the target framework has the same HTTP ports open, and it's more of a health check. But the smoke tests in our benchmarks also capture if messaging works correctly, if database updates, commits, and rollback behave as expected. And for apps that have a browser endpoint, we also have playwright tests that ensure that the user actions on the migrated application look identical to the source app. In doing this, we also evaluated a large number of coding agents. More results are in the paper. We discussed some taxonomies, failure modalities, but a quick highlight here is that although agents are really effective at migrating applications, ensuring that they compile and they can deploy, they're not really good at maintaining the behavior in the target application. What we noticed is after migration, only 2 to 14% of the migrations actually had the exact same behavior that the source application had. And compilation itself was a weak signal because that gave us a false indication that the agents are really good at migration, but the behavior was not preserved. And the flows here also strongly suggest that some frameworks are really hard to migrate to, and some frameworks are really hard to migrate from. So there is an inherent complexity and asymmetry in how agents migrate from one application to another. There are more details in the paper, various failure modalities, and some instructions on how agents can be better built. So here's a benchmark. Feel free to reach out to me after the talk. I'd be happy to answer any questions. Right? Thank you.
Now we have Grace Tang, AI at Hex on data benchmarks, where everything's made up and the points don't matter.
Hi, everyone. I'm Grace. I do AI research at Hex. We are a AI data analytics platform. And as such, I spend a lot of my time basically trying to get LLMs to do data analytics and data science better, which is really hard. And so a big part of what we think about is evals and experimentation. And lately, every time I look at a new public benchmark for data, I'm kind of struck by the same thing. Everything's made up, and the points don't matter. Roll credits, we're done. I'm just kidding. But what do we really mean by this? Well, today I'm going to talk a little bit about data benchmarks, where they are doing well and where we might be missing the mark. My thesis on benchmarking agents is very simple, and it's very much like what a lot of people talked about today. We should be testing these agents in environments that have the same level of realism as their eventual deployments. And as you'll find today, data is a uniquely poorly modeled field in frontier benchmarking. So before we get into that, though, what does a real frontier benchmark look like? Y'all might have heard of some of these, like Program Bench. You're rebuilding a common code base from scratch, no internet, just docs. Running a vending machine business and then just evaluating your profit at the end. Or like these simple yet challenging web search questions. These are actually only around 30% solvable by humans. What do all of these great frontier benchmarks have in common? Well, they're evals that actually test real-world behavior that we care about these agents being able to do. The problems are hard for agents, and they're hard for people as well. Now, though, let's take a look at the field of data analytics. DSBench. Last year, OpenAI used DSBench to report that their agent surpassed human performance by a significant margin on realistic data tasks. Ready to see what these realistic tasks look like? Well, a bunch of them are like these multiple choice exam questions about financial modeling. It's literally like, can you write the SQL? Can you tell me what Excel formula you should use? And then there's like a bunch of public Kaggle projects, including like this Scrabble word puzzle. It's totally crazy. And I think data analysts will tell you that this is not what their work looks like on the day-to-day. If this is what your work looks like, I'm sorry. What about Spider 2? I think Emily from Scale mentioned this one earlier, but we have a number of text-to-SQL benchmarks. These, though, I think the main issue with this is that it's not really testing analytics. If you look at it, the English is very specific, it's very prescriptive. You're basically just mapping like English to where clauses. It's like a translation task or an instruction following task. And the external knowledge is not exactly carefully curated either. It's the wrong sport. What about DabStep? This is a well-known set, and this question looks very straightforward. It's like, pick a multiple choice question, what's the top country for fraud? The problem, though, is that if you actually pull the data for this, the question is kind of fundamentally underspecified. It doesn't tell you whether you're looking at fraud rate, fraud volume, and like a real data analyst might produce something that looks more like this chart, and arguably that's more complete and correct. And so all of this is very hard. I don't want to dunk on everyone's work. They've done a lot of hard work here. But overall, these themes tend to emerge. 9 is too many for me to read out loud, but the main idea is that they're not realistic. These grading is really, harsh, it's grounded, not really in reality. So at Hex, we have built Shorelane. Now, Shorelane is completely made up. The points don't matter either. I'm not saying we figured it out, but it is pretty cool, and we try and address some of these realism issues. We built a fully synthetic B2B SaaS company called Shorelane Commerce. It's got a lot of semantic pitfalls that might occur in a real business. It's messy, it has migrations and incomplete documentation. And the task? Well, we have these agents do realistic tickets that an analytics agent or analytics person in real life might do. We evaluate on the entire train of thinking, on the tool efficiency, and the actual analytics that's going on. And still, though, this is only half the problem. These evals are still suspended in a moment in time. How can we allow data analytics to learn from their mistakes? Well, unfortunately, that's pretty much the time I have for today. So if you're interested in hearing more, please follow us at hex.tech. You can also always reach out. And if you're interested on working with us, please reach out at our careers page. Thank you so much.
And now we have Arindam Set, Principal ML Engineer at Genentech on AI Data Readiness Evaluations Framework.
Hi, everyone. I'm Arindam, and I'm a Principal Machine Learning Engineer in Genentech. My focus areas are Agentic AI, Scientific AI in life sciences, and AI data readiness, and also agent evaluations. So today I want to start with, I have one single argument about AI data readiness, is that as we are evaluating the agents, we also need to evaluate the readiness of the underlying data layer. So this is how it goes, at least in Genentech Roche. We are mandated to build an agentic AI system. We choose some data sets, and then ML engineers, AI engineers are working on it. A couple of months, we put some work together, put the framework together, and then when it comes to evals, we see it's not performing very well. And then we were wondering what happened, what went wrong. I mean, we went with, we went to all the LangChain blogs, all the Pydantic AI blogs. Hopefully we actually applied the best practices, but wasn't performing. Then we look into prompt engineering, we hope for the better models. But what we realized later is that the agents are not performing in a vacuum, right? They are working on top of a data layer. And the underlying data layer is something we need to also look at. I'll give a couple of examples, and then I'll go into a little more detail on that. Think of like there was this particular example where we had a data layer which was oriented towards more like dashboarding and reporting. And when we put an agent on top of it, what happened is that it was not performing well, and then we saw that it was oriented towards data warehousing or reporting or dashboarding. So that is something we need to look into. Now, looking into this, what we have come up with is an agent AI data readiness evaluations framework. And what we are calling it, at least as of now, it's an evolving framework. There are 5 dimensions to it. So from left to right, clockwise, the first is data quality. It's kind of obvious, right? How sound the data is technically, right? In terms of completeness, consistency, and freshness. Then semantic and metadata. Do we have metadata for that data set? For example, let's say we are dealing with a PostgreSQL database, and do we have table and column comments, or do we have a blob for containing the context of that? Access and governance. Can we access the relevant data at all, or the agent can access the relevant data at all, or not? Structural readiness. This is where I was giving that example of the data heroes database. What we found out is that the data mart actually had a concept of entity attribute value, and you can look it up what it is. But the bottom line is that that is not very conducive to running agents on top of it. Then we have also generalizability, where we are looking into like whether the agent, the data layer is generalizable, or can it go beyond the happy path. So with that, what we have done is we have actually recently got a NeurIPS workshop. I know Scale AI also has another workshop approved. Congratulations for that. We have a NeurIPS workshop approved in Paris, and we're looking forward to talking more about it. And basically what we are doing is putting the community together who are building data infrastructure for Agentic AI, and we're also building the evaluations and benchmarks for Agentic AI. So you can look into the website. Feel free to scan the QR code, and then. So this was truly a collaborative effort within Genentech and outside academia, industry, and outside community. And we're also looking to continue this conversation in the NeurIPS workshop. Thank you.
Now welcoming Scott Clark, co-founder, CEO of Distributional, how better evals can bring abundance through accelerated scientific discovery.
Hey everybody, thank you all for sticking around. I know it's Sunday afternoon and this is the penultimate talk. As soon as my slides come up, I'll look forward to chatting to you guys about bringing better abundance through better evals. Excellent. So as was said before, my name is Scott Clark. I'm co-founder and CEO of Distributional, and I'm building Talaria Scientific. And I'm going to tell you about how you get better abundance. But first, I'm going to define what that means. So what does abundance through AI mean? In my mind, it's better scientific discoveries that lead to new materials, more efficient energy. This leads to better medicine, more efficient ways of travel. It basically means living in a sci-fi future. It's less about how do we get rid of more white-collar jobs and put everybody out of work, and it's more about how do we improve people's quality of life. And I believe that for the first time, we're finally able to meaningfully accelerate scientific discovery with AI. The last few months have really unlocked quite a bit of capability. And this has been a passion of mine for a long time. I've been trying to solve this problem for the last 20 years of my career, with varying degrees of success. It started back when I was doing undergrad and leading up to my PhD, where every single problem that I solved, every single group that I worked with, from protein folding to quantum mechanics simulation to metagenome assembly, always ended with the same problem at the end. We'd build something great, and then we would need to tune it. Lots of different knobs and levers, hyperparameters, whatever you want to call them. If you could make the graphs and the benchmarks slightly better, you got a better paper. We jokingly call this grad student descent because it was often the role of the grad students to sit up late at night, kind of tuning knobs in a high-dimensional space, trying to get that slightly better paper. People did apply smart techniques to this, simulated annealing, genetic algorithms, local methods. I fell in love with Bayesian optimization, and that became core to my PhD thesis. And it ended up being the central point of my first AI startup, SIGOPT. Started this in 2014, and our goal was to solve the parameter tuning problem. And over the course of 7 years, we worked with great firms like Netflix tuning the recommender systems, Amex tuning their fraud systems, OpenAI in the early days when they were a nonprofit lab, tuning their early RL systems, as well as about $1 trillion worth of hedge funds, and several hundred academics used our free program to tune their papers, everything from materials design to drug discovery. When I sold the company to Intel in 2020, we used it to tune everything from chip design to benchmaxing MLPerf, when that was what everybody was overfitting to at the time. So the goal was optimization at scale for problems that really mattered. And it worked really well, except when it didn't. So the problem was it would fit exactly what you told it to do. It would always optimize what they gave us, but oftentimes when customers would come back, they'd say, yeah, you made that number go up, but some other number went down. And that's the problem with an optimizer. The very best thing about a black box optimizer is it will optimize any eval you give it. And the very worst thing about a black box optimizer is it will blindly optimize any eval you give it. And so you could make a really accurate fraud detection system if only 1% of your transactions are fraud by saying, nothing's fraud. 99% accuracy right there. Additionally, we're still a long ways from just setting these systems up to be completely autonomous. I think we're a long way away from just saying, goal, solve stable fusion containment, solve cancer, these sorts of things. And even if the model came back with something, how could we trust it? And that's the other side of this coin. You need to optimize these systems, and you need to trust them. And that's what I set out to do with distributional. I thought I would attack this in the most complex mathematical way possible, big statistical tests, and we would solve chaos, and we'd solve non-stationarity. And this was a terrible idea, because nobody likes tests, they didn't have the data, and everybody was just YOLOing models into production anyway. So I pivoted the company. This is what you do. You're failing, pivot. Analytics. So let's catch the evals that are sneaking through your system. How do we find patterns in behavior in order to be able to say, hey, this is the unknown unknown, the eval you should have written. This also failed. This is a really good idea, but it's more of a feature, let alone a product, let alone a startup. So now what I'm doing is I'm applying everything that I've done in the last 20 years to attack the scientific problem of how do we accelerate science focusing in on what actually matters, building bespoke evals that know physics, that know about the scientific research process, that know how to do hypothesis validation, so you can spin the flywheel of a what-if machine faster and faster and faster, doing what I did in grad school that used to take 6 months in 6 hours instead. If you're interested in this, we're building this in the open. It's going to be open sourced at NeurIPS. There's a private beta right now. Follow along, and I would love to chat with you if you're building anything computational science related.
All right, thank you folks for sticking around. This is the last talk for today with Ayush Agarwal, product lead at Uber on evals, the engine for agent improvement.
Awesome. Well, give a round to you all because you're here till the end. This is a full day event, and I'm really proud of you all for being here. So just thank you for being here towards the end. I'm well aware that I am the one who's in between you all from being here and a beautiful Berkeley day outside. So let's try to warm up the room and see who's here. So firstly, super simple one. Who took an Uber today? Quick raise of hands. All right, we have a few. That's great. But more importantly, who actually wrote an eval for an agent in production? Let's see who are the real builders. All right, okay, cool. And now the last one, and you have to be proud of this. Did those evals tell you something that changed the way that you shipped your product? All right, great. Great, so the difference between having evals as a checkbox versus an eval actually changing your product direction, that's what we spent over a year at Uber trying to make sure that every agent team was able to do. And I'm going to talk to you all about that today. So at Uber, we've been shipping agents throughout our ecosystem, both for external agents, so you can book a ride through your voice, as well as internally. And the thing that's powering all of that at enterprise scale is our Uber Agent platform, which I manage. And there's a bunch of different components across that to help agent teams not worry about the infrastructure. And the thing that I'm going to talk about today is evals, which is what this room is all focused on, which is really exciting. So one thing that we saw across the board is that every team wanted high-quality production agents, but they started to do one common thing. They said that, hey, let me just ship the agent, and I'll think about evals later. And it was a very rational decision because for them, they just wanted to go prove product market fit. They wanted to see if it even worked. But what that did was that then they got caught in this relentless loop of retrofitting evals later and trying to figure out why did that agent break. And so what we found was that there were true friction points that teams had that were preventing them from getting to that state earlier on. And we as a platform team decided to make that frictionless for them. So let's talk about those to make evals default. So the first thing, and this was kind of mentioned across the board, is the starting is tracing. And so what we did was we made sure that as soon as the first development started, they had tracing at every single environment. And what that allowed teams to do is understand and have a foundation for setting up the rest of their evaluations. They could just build an agent, vibe with it, send it out, and all of the information of how it's been changing over time is there and not something they have to add retrofit. The second was that once they were able to get insight, able to get their data, how to get insights out of it. Teams didn't know how to start with developing an eval. They didn't know what was the best way to write it or where. And so what we did was that we had the context of how the agent was built, the documentation around it, and we figured out what is the best starter kit evaluators and sent those insights directly to the builders in Slack so that they could understand, hey, I don't know what an LLM judges, but I do know what it means to have a tool contradiction and make a change because of that. What we also saw is that evals with agents is very different. They are not QA tests that are purely engineering, but we needed to bridge that gap so that the teams that are closest to the customer, like product and customer teams, had an ability to understand those. CLI experiences really democratized that. And so by building skills that managed the eval, we saw that teams were able to allow their product teams to own this entire process. Finally, this was something that we couldn't build a tool away for. It was changing the narrative around what an eval is meant to do. So we changed teams' narratives from, hey, is your evals 90% plus, to, do you actually trust your evals? What have you done and changed about your roadmap because your evals have told you that? And how quickly have you been able to update your data sets? Is your data set five months old and not really up to date with your product? All of this helped us ship products faster and catch issues much earlier in the product lifecycle. So what we're launching really soon is a rider voice booking in Uber. And what we saw with our evals was that although we had a 95% plus offline eval, when we saw a production eval showing us that the number of turns per session were way higher than average, we looked into that deeply and saw that, hey, there's actually a customer that is trying to book a ride to SFO, but somebody in the background said, hey, I want pizza. And the agent took that as an input and started rerouting them to the nearest pizza space. And so we realized that we needed to have the agent understand true intent and have no ops where it was not needing to be listened to. So that was only possible because we had evals as well as the products teams in the loop. So this is the evolution we had at Uber, where we had evals as the default come in because of these interventions, and now we're moving to evals as this engine. And this is where we're really excited, where traces go into failures, which are automatically categorized and then get proposed as updates to the agent, to the evaluators, and the teams are basically accepting and rejecting that. And that improvement feedback loop is what really helps teams bring agents that customers really love. And so that's the difference between having an eval metric that's a score for something that you know versus an engine that helps you continuously improve agents tuned towards what the customer cares about. That's what makes each of your trips magical at Uber, and we're excited to continue building this out. Thank you.